of the day to you all. I welcome you all to the day 3 of this lecture workshop. To begin with the first session, today we have with us Professor M.V.N. Murthy, and the topic is Solution to the Puzzles, Introduction to Neutrino Oscillation. Over to you, sir.
Thank you very much. Is this screen visible to everyone?
Sir, visible, sir.
Okay. And how is the audio? Is it clear?
Yeah, it's clear, sir. Clear, sir.
Okay, so let us start. And yesterday we talked about the disappearance or the deficit of neutrinos coming from the sun and also those which are produced in our own atmosphere. So we will continue from there. Yesterday I talked about the experimental results and the age-old problem, almost 150-year-old problem of how the sun shines. So today we will look at what exactly is happening. But in order to do that, I want you to remember the following properties of the neutrinos. Here is the standard model. Standard model is constructed with leptons and quarks and their interactions mediated by gluon, photon, and W plus minus and Z boson. Gluon for the strong interaction, photon for the electromagnetic interaction, W and Z bosons for the weak interactions. And of course, the Higgs is also there now. We have seen it. So, and that is the one which gives masses to all these particles. Now, I want you to focus on the leptonic part. Can you see the arrow as I move it? Can you see the cursor?
Yes, sir. Yes, sir.
Okay. So please follow the cursor whenever I am pointing to something. Now here, the leptons are in 3 flavors or families. There are 3 types. These are sometimes also called generations. There is the electron flavor, which consists of the electron and the electron neutrino. Muon flavor, which consists of muon and muon neutrino. And tau flavor, which consists of tau, lepton, and the neutrino with the lepton tau flavor. These 3 families, in fact, they share almost all their properties except that the muon and the tau are heavier versions of the first generation or the electron flavor. Now, within the standard model, all the neutrinos are taken to be massless. While electron, muon, and tau neutrinos, tau leptons have masses, the neutrinos are massless as far as the standard model is concerned. And there is another important thing, which is the conservation law, that whenever an interaction involves a nu E in the initial state, then this electron flavor is conserved, which means that this nu E can, of course, go into nu E itself when that flavor is conserved. But in so-called charge exchange interactions, this nu E may produce an electron. But even though charge is conserved, it cannot produce a muon. This is known as the lepton number conservation in general, but in particular, within each generation, the flavor content is maintained. Now, this is as far as the standard model is concerned. So we are now going to go beyond the standard model. All the properties that we are going to talk about now will involve properties which are not contained in this nice cartoon of the standard model. So let me go back to where we were yesterday. So we completed the solar neutrino problem and the atmospheric neutrino problem. And I said that today we will talk about a solution to all these problems. Now, as I mentioned yesterday, any solution has to come from neutrino properties because the deficit is seen not only in solar neutrinos, but in atmospheric neutrinos also. So therefore, it is not a property of the source that we don't understand, but it's the property of the neutrino that we need to understand, going beyond what we already know in the standard model. Okay, so going back again, remember that there are 3 flavors of neutrinos, nu e, nu mu, nu tau, corresponding to their charged particle cousins, electron, muon, and the tau. And whenever we talk about particles, of course, there are always their antiparticles. So in a nutshell, the solution that we are going to talk about is oscillations that result in the change, a mechanism called oscillation that results in the change of flavors as neutrinos propagate through space. Which means if you have some n number of neutrinos of electron type, maybe as it is traveling in space, it will get converted. Part of it is getting converted into, let us say, nu mu. And what is remaining goes as nu e. And if my detector can only detect nu e, then I will see a deficit of the electron neutrino flux as compared to what is produced in the source. Okay. So this means that the flavor is changing. Now already we see in this mechanism a deviation from what is already contained in the standard model. Standard model doesn't have this property. So this oscillation that we are talking about, where the flavor changes as the neutrino propagates, is a new property. It is beyond standard model. And we will show how one can construct a quantum mechanical scenario in which this can be achieved. And I'll also tell you why in the end it fits the data. Okay, next. So here is what I'm going to tell you. This is a very simple quantum mechanical thing to begin with, but as we go along, you will see that it has a lot of important physics in it. So neutrinos, we will show that if the neutrinos are massive, that means they have different masses and mix. I'll explain what this mixing is. Then they exhibit a quantum mechanical phenomenon called flavor oscillation, which I mentioned before. Now, there may be many flavors of neutrinos. In the standard model, we have 3 flavors. These are called 3 active flavors of neutrinos. And it's very complicated to involve all of them at the same time. I'll come to that a little later. So for simplicity, what we should do is just consider 2 flavors. Assume there are only 2 flavors. Let us call them nu e and nu mu. Okay. Now I will just define this nu e and nu mu in the following way. This nu e is a mixture of nu1 and nu2. I'll tell you what this nu1 and nu2 is. So, and nu mu, since there are 2 states, we consider 2 other states called nu1 and nu2 and mix them in the following way so that it maintains its orthonormality. So, nu e, nu mu overlap is 0. Similarly, nu1 and nu2 are orthonormal states, quantum mechanical states. And you can see that this looks simple, like a simple rotation of the basis, where you go from one basis called nu1 and nu2 to another basis called nu e and nu mu. In fact, you can write it in the matrix form, a column matrix nu e nu mu, and a matrix cos theta sin theta minus sin theta cos theta operating on a column matrix nu1 and nu2. So this is, if you look at that matrix, you will see that it's the familiar rotation matrix in a plane. Now this theta is a parameter we don't know. So at the moment, at this stage, we are not doing anything new. We are just changing the basis with theta as a parameter. So it's a fixed rotation. Theta is a fixed parameter. We don't know what it is. Now at this stage, it appears like change of basis, but this nu1 and nu2 are the states which are solutions of, say, Schrodinger equation. In which case, they evolve in the following way. Nu I of t, where I can be 1 or 2, evolves as exponential of e to the power minus I, eit, operating on nu I at time t equal to 0. So if you know nu I at time t equal to 0, this evolution tells you what the state will be at time t. Now, in a simple change of basis, this E is common to both and therefore nothing happens. Now, let us say that this EI is something which refers to nu1 and nu2 which have slightly different masses m1 and m2. Even if their momentum is the same, they are momentum eigenstates, and even if their mass is slightly different, then this phase will be different for nu I, nu1 and nu2, and therefore when nu1 and nu2 evolve, they evolve with different phases. The phase that it acquires during the travel will not be the same. This is a very important property. I'm here using what are called as natural units, which means that I set c, velocity of light, speed of light equal to 1, so that all the other speeds are measured in relation to this c. So therefore, it will be, if it is a massive particle, it cannot have c equal to 1. It will have a speed which is less than 1. So they all become ratios when I set c equal to 1. And you know from relativistic energy equation that the energy can be written as E equals p squared c squared plus m squared c to the power 4. This m is the rest mass. Now when c is equal to 1, we simply write it as EI is equal to p squared plus mi squared. Okay, so this is to clarify the notation that I am using, and please remember this. Now, since the phase acquired as so these are called as the energy eigenstates. So what is it that we have? On the left hand side, we have two flavor states which are defined in the following way for a fixed theta. So this defines our flavor state, nu e and nu mu, and nu1 and nu2 are the states which come as solutions of the Schrodinger equation, and their time evolution is given by this in vacuum when there is no other interaction. This is the way they evolve with time. So now what happens? So if you look at the neutrino propagation, so let us start at time t equal to 0. The neutrino is that a question? Shall I continue? Okay, so let us consider now the neutrino propagation. So let us start at time t equal to 0, where the neutrino is produced in a flavor nu e, electron neutrino, like the sun. Okay, so we start at time t equal to 0. So at time t equal to 0, it is produced as electron neutrino, therefore it is given by this combination. That is fixed, that defines our electron neutrino. Now after a time t, what happens to the state? Nu e at time t, that's the flavor state, is cos theta e to the power minus I e1 times t nu1. That is how the nu1 state evolves. And the nu2 state evolves as e to the power minus I e2 times t. Now look at this. There is a phase here and there is a phase here which are not the same. If it's an overall phase, we can ignore it and we can take it out because it doesn't affect the probabilities. But this nu1 and nu2 have acquired slightly different phases. So which means that so-called electron neutrino flavor, which is produced at time t equal to 0, as it propagates, has changed itself. It has changed itself in such a way that it has acquired a phase difference between the first term and the second term, which is given by the difference in these energies. So how do we know then how much of this evolved nu e of t contains the original nu e flavor? Because this is the electron neutrino. This is the evolved electron neutrino flavor state. So how much of this is this original electron neutrino? So quantum mechanics tells us how to do this. You just take the overlap between these two states. Okay, so that overlap is an amplitude. In fact, it is probability amplitude A. Going from 0 to t, this amplitude is nu e at time t and nu e at time 0. So you take this overlap, and as you know that these nu1 and nu2 are orthogonal states. So therefore, nu1 with itself is 1, nu2 with itself is 1, but nu1 and nu2 bracket is 0. So therefore, you get cos squared theta times I e1 of t, because I have put it as on the left hand side here, and this is sine squared theta times the phase e to the power I e2t, conjugate of the phase that you see here. So this is the amplitude of the transition from the original electron neutrino to the flavor state after time t. Now this is not the electron neutrino. It has already changed its phase. It started as electron neutrino, but this is different from this. And that difference, that information is contained in this amplitude. So now what is the probability? Now again, quantum mechanics tells you that. So the probability of the original flavor nu e remaining in this after time t is simply the square of this amplitude. So P, we denote it as PEE. It simply means the probability of electron flavor remaining as electron flavor is the square of this amplitude, which is given by cos 4 theta square of this, modulus square of this, which is cos 4 theta sine 4 theta 2 cos square theta sine square theta, and the real part of the difference between these two, which is 2 times cosine of E2 minus E1 times t. That's all. This is the probability, and it is a number which now depends on the parameter theta, which is the mixing angle, and the difference in the energies between E2 minus E1. Now notice one thing, that if the parameter theta is equal to 0, if there is no mixing, then this probability is 0. At the same time, if there is no difference in the energies, if nu1 and nu2 are eigenstates of the same energy, then again E2 minus E1 is 0. So therefore, the whole thing is 0 and no such phenomenon can occur. No such phenomenon of change of flavors can occur. So let us go ahead with this. You can write this probability in a nice form. Okay. So in fact, what you do is you take cos 4 theta sine 4 theta 2 cos squared theta sine squared theta, and you can write this cos as 1 minus sine square E2 minus E1 t by 2. Then you take the first term 1 together with this, and then what you get is 1. And then you have 2 cos squared theta sine squared theta, which is actually sine squared 2 theta. And the phase comes as sine squared E2 minus E1 t by 2. The phase does not depend on the sign of E2 minus E1, but only the difference, because it is sine squared. So now what is this difference in energy? We started assuming the neutrino masses to be very small compared to the energies. Now, the laboratory experiments, the limits on neutrino masses is of the order of an electron volt or even less. So that is the limit on the absolute masses of the neutrinos that we have. But what are the energies that we are looking at? In the case of solar neutrinos, we are looking at millions of electron volts as the energy. And in the case of atmospheric neutrinos, the energies are even more. It is 1,000 million or a GeV or more. So the energies that we are looking at of neutrinos is far greater than whatever that non-zero mass could be, which we don't know, but we know that it is very small. So therefore, we can make an approximation of the square root. We can expand the square root and make an approximation up to expand it up to the first term and take that. So E2 minus E1, just doing the simple binomial approximation. So if you do that, the first term is P, that gets cancelled, and then you have m2 squared minus m1 squared by 2p. That is the term that is the leading term that survives, and we write it normally as delta by 2e. My notation here is slightly different. Normally standard notation is delta m squared. So since I am doing in this LaTeX, I felt lazy to write it every time. And there is a question, what is a flavor state? Now this is what I explained earlier. A flavor state is defined by the superposition that you have this of two mass or energy eigenstates. Now, why do we distinguish the flavor state? Because it is these flavor states that are produced in weak interactions. These are the states that participate in the weak interactions. However, they are assumed at this stage to be mixtures of two energy eigenstates. So these energy eigenstates differ in energy through the mass of the neutrinos, which are assumed to be different, as I showed here. Is that okay? Then this delta, usually sometimes people write it as delta m squared. I am a bit lazy, so I just leave it as it is. And now you can see that after making this approximation, this delta, you should remember, is not the mass difference, but the mass square difference, because that is what comes after you make the binomial approximation here. Okay? So take that difference, call it delta, and this is 1 minus sine squared 2 theta, that is the same. It's a parameter that is given, so its value is fixed. But then you have sine squared delta by 4e. I replace this time by because neutrinos are almost relativistic, their mass is so small, you can say that the length traveled, the distance traveled by the neutrinos is simply c times time. And since we have assumed c equals 1, I can replace the time elapsed by the length L. Okay. Now, this question here about the flavor state, it continues. Sir, that angle in the expression represents Cabibbo angle. It is similar to Cabibbo angle, but it is not Cabibbo angle, because Cabibbo angle is used in the case of mixing of quarks. The down quark and the strange quark mix in weak interactions through the Cabibbo angle. This is very similar to that, but this is in the lepton sector. So you can think of this theta as the equivalent of Cabibbo angle in the lepton sector. Is that okay? Yes, that's a very good question, and it is like Cabibbo angle, but not for the quarks, but for these things. Okay, Amol says electron neutrino, muon neutrino, and tau neutrino are flavor eigenstates. Yes, that's correct. That is what we are referring to here. Okay, so now let me continue. Many clarifications will come to you in the chat through Amol and Vivek also. So let us keep going. So notice that the second term is an oscillating term which depends on the ratio of length, distance of propagation, and the energy of the neutrino at the source. So there is an energy dependence in this probability. So this is the flavor survival probability of an electron neutrino. That means how much of the original electron neutrino survives after propagating a distance L. Okay, so this is called as the survival probability. But what happens to the other part? Remember that this probability is less than or equal to 1 by definition. In fact, if you can see here, both terms are bounded by 1, and it's a difference of two terms, which are, the first term is 1, of course, and this is bounded by 1. So therefore, it is probable. If you look at the overlap between the two states, not just nu E upon nu E, you look at overlap between nu mu, evolved state nu mu with the nu E, then you will get the following relation for that probability when you do the amplitude square, that is nu mu at time t and nu E at time t equal to 0. It is simply sine squared 2 theta and sine squared delta by 4E L. Now this is precisely the term which is appearing here. So whatever has disappeared as electron neutrino has appeared as muon neutrino. So this is the oscillation probability. It's called oscillation probability because although this term is a constant, this term is a sine squared delta by 4E times L. It keeps oscillating because sine is an oscillating term and sine squared is also an oscillating function. So part of nu E, therefore, if this probability is less than 1, will appear as nu mu. But remember, we are only considering two flavors, electron neutrino and the muon neutrino. And therefore, the total number or probability is conserved. That is PEE plus PE mu is equal to 1. So that means if you put together all the surviving electron neutrinos, and if you can also see all the flavor oscillated muon neutrinos, then that sum should be equal to 1, which means the total flux will remain the same. Now here is a cartoon of what we have talked until now. So remember, we started with flavor states, electron neutrino and muon neutrino, rotated from a basis which is nu1 and nu2. Then we said let us have nu1 and nu2 with slightly different masses, and therefore it is not a simple rotation which would be just change of basis, but it's a little more complicated than that, and that leads to flavor oscillations. So you start in this color yellow and red, mix them, and this is your electron flavor, and you mix them this way, it is your muon flavor, that means muon neutrino, electron neutrino. And here the propagation is shown for a pure nu mu. You can also convert it into pure nu E by changing the colors and other values. So you start with this mixture of red and yellow given by cos theta and sin theta, and as the time evolves, the phase of these two keep changing, and because there is a phase difference, and since that phase difference is time dependent, you see that they keep on spreading out, coming together, and at some stage it may come back to its original state, and at some stage it may just look like the electron neutrino. So therefore, if you follow these oscillations through, then you will see that what you are seeing is a flavor oscillation of electron flavor to muon flavor to electron flavor, and in between it could be a mixture of both flavors. So hence, if this mechanism is true, then as the neutrino travels to the earth from the sun, it keeps oscillating between different flavors of neutrinos. And if the detector, now comes the most important part, if the detector is designed to see only electron neutrino, because we thought that we didn't know about oscillation, we knew that the sun only produces electron neutrinos. So I designed the detector only to see the electron neutrinos. Then what happens if this mechanism is correct? Then you may see, depending on the distance and energy, a part of this electron neutrino flavor has actually gone away as a muon neutrino flavor, and therefore it results in a deficit. Okay, so this is what happened in Davis experiment. Actually, Davis's detector could only see the electron neutrino. It had no ability to see the muon neutrino because one, the energy of muon neutrinos is also, the converted muon neutrinos also have the same energy as the original electron neutrino that is in the MeV range, and the detection is done through some charge change interactions. I'll talk about it a little later, which requires looking at charged particles called muons, which are produced by muon neutrino. And those muons, charged particle muons, mu minus, will have a mass of 105 MeV. So the energy is insufficient even if we can see these ions. And of course, since they cannot produce, nu mu will pass through as nu mu, and there is no way we can detect the neutrino directly unless it interacts with the matter. In this case, Davis's detector detected electron neutrinos through its interaction with 37 chlorine producing the argon atom. So therefore, it's really that the detector could not see the electron flavor. So that is the possible explanation using this scenario. But it's a little more complicated than that, because the neutrinos are produced in the core of the sun. So therefore, they have to pass through almost the whole radius of the sun before they come into before they start propagating in vacuum. And then when they come to the earth, sometimes they have to pass through at night whole diameter of the earth to reach the detector. And during the daytime, of course, they can interact with the detector directly because the atmosphere is very thin anyway. So we not only have vacuum propagation, we also have neutrinos propagating through matter. However weakly interacting these neutrinos are, they do interact, and the matter provides a certain material with which it interacts, and therefore we have to take that also into account and see if it can make a substantial difference. Now here I will have to give you a little more involved explanation. So if you do not follow the math here, because lack of board makes me a bit nervous here, because I can't explain and work out everything. So, but in the end, I will tell you what is happening in a nutshell. So keep your attention on what I'm saying here, and in the end, we will see what is happening. So neutrinos passing through matter feel interaction with electrons in matter. Electron neutrinos interact with electrons, and all neutrinos in fact interact with electrons in matter. So for example, if you take an electron neutrino, it can interact with the electron present in matter and produce an electron and have an electron and an electron neutrino in the final state through what is called as a charge exchange reaction, where this electron neutrino gets converted to electron and the electron gets converted to electron neutrino. So all conservation laws are fine, except that you will see that there is a charge change at the two vertices. This is what is called as a Feynman diagram. I'm not going into the details of that. You can think of this as a schematic of what is happening. But they can also interact in what is called as the neutral current interaction. This is nu x. X can be electron neutrino, muon neutrino, or tau neutrino. This nu x can just go into nu x, and the electron in the matter simply goes into electron. This is just a scattering. There is no charge exchange. And in fact, what is exchanged? The exchange particle is the Z boson. And the exchange particle here, where there is a charge change, it is called as the W boson. And this W and the Z bosons are the ones which actually mediate the weak interactions. Okay, so there are two types of interactions: charge current and neutral current. Neutral current is common for all the flavors of neutrinos, and in fact it has the same strength, same probability. Whereas for electron neutrinos, there is a special interaction called charge current interaction, which allows it to have a slightly different interaction compared to all other neutrinos. Now, if there is something which affects all the neutrinos equally, this is something we can ignore because this will not contribute to any flavor changing property during oscillations. But this affects only the electron neutrino. Therefore, this is very important. The analogous thing that you can think of here is like when the electron, when the photon goes through, when light goes through matter, actually the photons, the particles of light, interact with matter. At a classical level, this interaction is taken into account by the refractive index. And for those who are familiar with the property of birefringence, the refractive index actually depends on the color and it changes from one color to the other. So therefore, sometimes you get different different colors passing through the medium, coming out differently from the way compared to the way they entered. So the property of birefringence of photons and the fact that they have a refractive index is a result of the interaction of the photons in the matter. So what we are talking about neutrinos here is very similar to the property of refractive index. We are talking about the refractive index of the neutrinos as they travel through matter. Now, because of these interactions, and since this interaction is special for electron neutrinos, you can think in analogy with birefringence that the electron neutrinos have an extra potential in the matter compared to, they feel an extra potential in the matter compared to all other neutrinos. Now, how do you calculate this potential? Now, that you have to do using the interaction Hamiltonian. And this is, for those who are not familiar, you don't worry about it. This interaction Hamiltonian, using the properties of these electrons, which are in the atoms, they are almost at rest. And therefore, we can make a non-relativistic approximation of this Hamiltonian. And you can write it in terms of the electron density in matter. So the effective potential which comes from this Hamiltonian, interaction Hamiltonian, written this way, is given by this VCC. This is the extra potential coming in the matter over and above what all other flavors of neutrinos experience. And this is special for electron neutrinos. And it is given by √2 derived from here is √2 times GF. And GF is the strength of weak interaction, and it's called as the Fermi coupling constant, and multiplied by the number density Ne of the electrons in matter. This is the number density of the electrons in matter, and it depends on what the neutrino is passing through. The electron density in Sun is different from the electron density on Earth. So therefore, this matters when neutrinos are going through matter. Okay. So for antineutrinos, if you calculate the same potential, and in fact, it's a very interesting thing that this sign of the potential is opposite to that of neutrinos. Electron neutrinos have this sign, and electron antineutrinos have a potential which has minus sign. This comes from the property that the matter is CP, not CP symmetric, but that's a different question. At the moment, we will not go into it. So now, how do you calculate the evolution in matter? This is a bit involved. If I have to go through it, I need a lot more time. So therefore, what I will tell you is that you can write the Schrodinger equation for the evolution of electron neutrino and the muon neutrino in the presence of matter. Okay. So this A is a term which includes the effect of matter. And in fact, it can be calculated to be 2 times energy of the neutrino times the potential that I discussed in the previous slide. And this is given by this 2 √2 GF. I change the notation for the density, small ne times energy. And of course, delta is the difference in the two mass squares of the two mass eigenstates in vacuum, not in matter. So therefore, you can write the evolution for flavor states. The potential appears in the flavor basis. Therefore, we converted the Hamiltonian to the flavor basis. And now we are looking at the evolution of these electron neutrino and the muon neutrino through matter. Now, what is the effect of this? Oh, what is the value of this? This A can be written as A into 8 into 10 to the power minus 8. The density as a number calculated in units of grams per cc times the energy which is given in millions of electron volts. So this has this kind of magnitude, and it can either decrease or increase depending on the density and the energy. Now remember, since the potential changes sign, for antineutrinos, this A changes sign. So now what you can do is that this is a matrix which is not diagonal. So therefore, to find out the evolution of this nu E and nu mu, this time evolution of this, we have to solve this equation by diagonalizing in the basis and determine this mixing angle. So like before, inside matter, we write the flavor state in terms of a unitary matrix U in matter times this I. Now F is E mu, stands for E mu flavors, and this I stands for mass eigenstates 1 and 2 in the matter, and this UM is a unitary matrix. In fact, for 2 generations, it's just a real matrix, which you can write as cos theta m sin theta m minus sin theta m cos theta m. This m subscript means that you are now talking about matter, but we are using everything as we did in the vacuum earlier, where we just had theta. And there was no need to diagonalize because this matrix was already diagonal. So now, if you consider what is this theta m, which diagonalizes this mass eigenbasis inside matter, then it turns out that this angle theta m is written as sin squared 2 theta m is mass squared difference delta sin squared 2 theta divided by delta cos 2 theta minus a whole squared plus delta squared sin squared 2 theta. So this is the mixing angle in the presence of matter with interactions, which depends on these parameters which involve the mixing angle theta in vacuum, the mass square difference delta in vacuum, which is a parameter. These two are parameters. And this A is something which is property of the matter, and it depends on the matter potential. So therefore, this theta m is therefore very different from what it was. This mixing angle in matter is different from the mixing angle in vacuum. Now, of course, if you put the potential equal to 0, that means A equal to 0, then you will see that this is simply delta squared cos squared 2 theta. And when you add these two, it just becomes delta squared. And I think I should have had delta squared here. I'm sorry. Then that delta squared cancels. Then sin squared 2 theta m is equal to sin squared 2 theta. Sorry, this should be delta squared. Please make a note of it. I'll correct it later. Okay. So you will see that when A goes to 0, everything goes back to vacuum. And this is in the presence of matter when this A or the matter potential is non-zero. Now, the conversion probability, we will just do what we did in the case of vacuum. So we just take the states and take their overlap as the electron neutrino is propagating in vacuum, and it just changes by this fact sin squared 2 theta we had earlier in vacuum, which is sin squared 2 theta m. Theta m is this angle which we have calculated. Then this sin squared pi L by lambda m, which is just a different way of writing whatever we had calculated earlier. And this delta m is simply the values, eigenvalues of this matrix in the presence of matter. These are the ones which characterize the mass eigenstates in matter. So, okay, so that is what we have. So we got the probability in matter, and we can do one more approximation just to see what is happening. This sin squared pi L by lambda m, depends on the energy and the length traveled. Now the neutrino is not produced at one point in the sun. Neutrino is produced all over the core, which is about 10% of the radius of the sun. So therefore this L varies quite a bit because it's an extended source, and therefore if if you take L by E, then that varies quite a bit. And if it is a rapid oscillation, then when we put together all the neutrinos coming from this extended source, this sine squared averages to half. When there are rapid oscillations and too many oscillations contained in this L, then it averages to half. And if you put that half here, this becomes the probability. So which is what is called as, some of you may be familiar, this is called as the Breit-Wigner expression for resonance if delta sine to theta is interpreted as the width. Now here I have put delta squared correctly. So, and this mechanism was first worked out by Mikhail, Smirnov and Wolfenstein, and it's called as the MSW effect in the case of two neutrino flavors. And in fact, Professor Smirnov here is still a collaborator of Professor Amol Digge. And this is MSW res. So why is it called a resonance? That this actually maximizes this. Remember, this A depends on the potential, and the potential depends on the density and energy. So therefore, this is a varying quantity in matter. So therefore, when it hits A equals delta cos 2 theta, then it becomes maximum, and therefore this is called as a resonance. And in fact, if you plot, you will see that it has that nice Breit-Wigner form. Yes, I heard a voice. Okay, if there is nothing, then let me continue. So, okay, let me summarize what happens. If you look at this probability, suppose the density at the center of the source, like sun, it's very large. In fact, it's something like 130 grams per cc in the center of the sun, which is actually 15 times the density of iron. The core of the sun is very dense. Let us say, if you are looking at supernova, it will be even higher. And therefore, let us look at some ideal limits. If the density goes to infinity, then what happens? This A goes to infinity. And then we see that the cos 2 theta m, the cos of the mixing angle in matter, actually goes to minus m, and this theta m is pi by 2. And when theta m is pi by 2, the mixing in matter will, the electron neutrino will involve only this nu m, nu 2, and not nu 1. So instead of being a mixture of nu 1 and nu 2, it becomes a pure state, nu 2m. And a pure state, when it evolves, nothing happens to it. It evolves as a pure state. So therefore, when this electron neutrino, which is produced in extremely high dense core, emerges out of the matter, then it will be produced in the state nu 2. And usually you put this m as a subscript because this mass eigenstate may also be changing as you go along. But there is what is called as an adiabatic approximation, in which we assume that it's changing so slowly that it emerges as nu 2 and a pure nu 2. And if the theta is small, then of course this nu 2 will be dominantly nu mu. So therefore, in the initial stages, when the electron neutrino is produced close to the center, all those neutrinos emerge more or less as muon neutrinos. Then there is a critical density where this theta m is pi by 4, because if A is equal to delta cos 2 theta, then sine squared 2 theta m is equal to 1. Therefore, their theta m is equal to pi by 4. Then electron neutrino is an equal mixture of both matter eigenstates, and as density goes to 0, it emerges as its original flavor, which is electron neutrino cos theta nu 1 and sin theta nu 2. So this scenario is in the adiabatic approximation. Okay. So now what we have said is that neutrinos which are produced below the critical density, or in the density regions which are higher, below in the sense of radius, that means close to the core, they disappear into some other flavor, and those which are outside of that core will emerge as electron neutrinos, and these will go further oscillations as they propagate from the sun to the earth through vacuum. So what we see in a detector on the earth is a combination. It's a combination of both matter effect as well as the effect of propagation through vacuum. So it's a combination of all these effects, and in 2 generations I have shown you 2 very simple situations. Both are about ideal situations, and in general it is much more complicated. So our story so far is like this, that okay, as when we consider the solar neutrinos, we have a certain flux of solar neutrinos which are emerging from sun, and when they come to the detector, we see that part of it has already gone away as nu mu, and part of it remains as nu e. And what we detected is that part which remains as electron neutrino, and therefore we see the deficit. But how do you know this is the case? Because we are only detecting electron neutrinos. How do you know that this is correct, this scenario is correct? In fact, I'm reminded of a story which Professor Rajshekaran always tells me, that it's like a painter who had an exhibition where a painting had just a frame and a blank thing inside, and the person who was going through the gallery asked the painter, so what is this painting? There is nothing inside. So the painter said it's a painting of cow and grass. Then he said, where is the grass? Then he says that the cow ate all the grass. And then the next question from this connoisseur was, where is the cow? Well, cow ate all the grass, grass is finished, and the cow went away. So this scenario is reminiscent of that nice story. But that apart, that was in later vein, of course. So if you have an experiment in which you can see not only electron neutrino flavor, but also the muon neutrino flavor, because you are saying that the deficit is because part of it is converted into muon neutrinos. Now, can you have an experiment which sees everything? Now, that is this beautiful experiment called as the 3-in-1 experiment, and it was done at the Sudbury nickel mine, and this collaboration is called as the Sudbury Neutrino Observatory, and their result appeared in 2002, though the detector they started building in late 1980s. And the original idea is due to a scientist, a physicist called Herbert Chen, who unfortunately did not live long enough to see the realization of his dream. And this was a beautiful experiment. So the experiment consists of 1,000 tons of heavy water contained in a 6-meter or 20 feet radius acrylic vessel. Here it is. It's suspended from the roof, and outside the vessel you have some normal water, and then you have the photo multiplier tubes all around. These photo multiplier tubes that you can see here are like the eyes. They are looking into the detector, and they can detect whatever happens inside the detector. And this experiment had the ability to look at electron neutrino scattering on electrons, the recoil electrons they could detect. Because it's heavy water, it contains deuteron nucleus. The electron neutrino can interact with the deuteron, produce an electron, and break up into 2 protons. It's a charge changing thing. This is also done. This is also possible to detect because both these electrons are detected through their Cherenkov radiation above a threshold of 5 MeV. And it had another very important property, that not just electron neutrino, but any flavor of neutrino could interact with the deuteron and break it up, just break it up without any charge change. So when you break up a deuteron nucleus, it consists of a neutron and a proton, and this proton gets absorbed. But the neutron, when it gets absorbed, it can again form a deuteron nucleus, or this neutron can be absorbed by putting some salt inside the detector as good neutron absorbers, which has a characteristic signal. Now, using that, by detecting these neutrons, they could identify the total number of events, no matter which flavor of neutrino was interacting in the detector. So, if you say that part of this electron neutrino is converted into other neutrinos, then this reaction will see it, and the experiment had the capability to do all these three detection reactions. Now, the first one is simply super K result. The second one in isolation is the Davis result. And together, the ratio of the expected events to the observed events, in fact, is 1.0 within errors, which means now you have established that you have seen the total flux coming from the sun, and the solar neutrino problem is finally solved. Okay, so now I have another 10-15 minutes. I told Vivek Datar that I'll give him a little extra time. So let us go back. This is the end of the solar neutrino problem. So oscillations explain this solar neutrino problem beautifully with matter effects also taken into account. And in fact, in a detailed calculation, you have to put everything. In fact, we have, separately looked at each effect. So it is not necessary. You can put everything. And in fact, you have to bring in the third flavor of neutrino also. And in fact, that can be done. That has been done by many people, including people like me, Amol Dige, and many other people in phenomenologists in India and abroad. Okay, now back to atmospheric neutrinos. We had a problem there. Okay, the problem was that the neutrinos are produced all around the Earth in the atmosphere, and most of them are produced at an altitude of about 14 kilometers. So therefore, if you have a detector here, SK detector, now the neutrinos coming from above will travel about 20 kilometers or 14 kilometers if it is directly above, and those which are coming from the other side of the Earth travel a very long distance. Now already we know that oscillations depend on the distance traveled. So therefore, if there are no oscillations, then what Super K calls as upgoing neutrino flux and downgoing neutrino flux should be the same. But their experiment found that it is different. Now, with oscillations, we see that it is not the same. Downgoing neutrinos oscillate differently from the upgoing neutrinos because they travel different distances. One, the distances are different. And the second thing, you look at the where they are going, this 10,000 kilometers, or if they are coming from below, is 12,600 kilometers, they are going through earth matter. So not only the distances are different, there will be different matter effects when you look at the atmospheric neutrinos from above and below. So the deficit is, as we have seen earlier, is direction dependent. I'll go back to the data in a moment. Upgoing neutrinos are only half of what is expected from the known flux, whereas there is no change in the downgoing neutrino flux. There is no perceptible deficiency in the electron neutrino, but only in the muon neutrino. And the muon neutrino must be oscillating, therefore, into something else other than the electron neutrino. Why? Because if muon neutrino, if there are only two flavors of neutrino, electron neutrino and muon neutrino, then this muon neutrino can only oscillate back to electron neutrino, and electron neutrino can oscillate to muon neutrino. And that scenario is very different from what we see in the data. There is no change in the electron neutrino flux, or almost no change. But in the muon neutrino flux, there is a perceptible difference when they come from above or when they come from below. Okay, so obviously the solution to solar neutrino may dominantly involve electron neutrino going to muon neutrino, whereas the atmospheric neutrino problem may dominantly involve some other flavor conversion. So we'll have to invoke a third flavor, which is, we know that it exists, that is the tau neutrino. So therefore, atmospheric neutrino may have a solution when the muon neutrino dominantly oscillates to tau neutrino. So therefore, we need to consider a scenario in which all the three flavors are there for a complete solution. So now, in a realistic neutrino mixing, of course, we have, here I'll just mention this. I will not work out anything because this is quite complicated. And even analytically, if you have to do it, then you will have to make some approximation. So therefore, it is unnecessary. So in a realistic case, let me make few statements. There are three neutrino flavors: electron neutrino, muon neutrino, and tau neutrino. These are the flavors, and they are mixtures of mass eigenstates nu1, nu2, and nu3. And that mixing is given by a unitary matrix, and that unitary matrix has a parametrization which involves first a 2 by 2 matrix, 2 by 2 submatrix of the 3 by 3 matrix, which involves angle 1, 2. That means this mixes electron neutrino flavor and muon neutrino flavor. And the third one, which is mixing muon neutrino and tau neutrino. And these two sectors are linked by another where 1,3 mixing occurs through this. This is about the most general parameterization of the 3 by 3 unitary matrix after absorbing some excess phases, which cannot be determined through these in this analysis. So now this realistic scenario will involve three angles and one phase, and this is called as the delta CP. The reason why it is called as CP is that because it comes with the exponential I, it's a phase, and it is also complex. So the most general parameterization involves three angles and a phase, which makes this a unitary matrix and not a rotation matrix as in the 2 by 2 case. So these are the oscillation parameters, and because this U is complex, when you go to antineutrinos, you have to take a conjugate of this U for the mixing, and this conjugation means that this phase e to the power minus I delta Cp changes sign to e to the power plus I delta Cp because it's complex conjugation, which means the sign of this phase is different for neutrinos and it is from what it is for antineutrinos. So which means this phase can distinguish neutrinos and antineutrinos, and this is, if it is non-zero, then it creates a different scenario for neutrinos and antineutrinos as far as oscillation is concerned, and therefore if it is non-zero, then it reflects the matter-antimatter asymmetry. Or in the case of neutrinos, the asymmetry between neutrinos and antineutrinos as they propagate. And that has consequences to matter-antimatter asymmetry. So this is a very important thing. So, but in general it is complicated. The solution to atmospheric neutrino problem also lies in the oscillation of nu mu to nu tau. Mainly, over distances and energies involved, the electron neutrino is almost unaffected. So let me show you the slide, and this figure which I showed yesterday, but I didn't tell you what it is. So if you put in this realistic three neutrino oscillations, you see the green curve. The green curve in the oscillation scenario passes through the data, and without oscillation you have this red curve. This is for the electron-like events, and this is for the muon-like events induced by muon neutrinos. And you see it is very dramatic. The moment you put oscillations, the green line goes through the data, and the red line, especially for those which are coming from below, is very, very different from what we see in the case of with oscillations. So this confirms the oscillation scenario also for the atmospheric neutrinos. And thus, it completes the solution of the neutrino deficit problem in atmospheric neutrinos and muon neutrinos, atmospheric neutrinos and solar neutrinos. And So here is more or less, the summary of the results, and I'll show you a diagram also next. The parameterization of this unitary matrix shown above is a convention. It's a standard parameterization. It's called the Ponte-Carvo, Maki, Nakagawa, and Sakata mixing matrix. Ponte-Carvo is the one who talked about neutrino oscillations in the very beginning, a person who has made extraordinary contributions to this field. All experimental analysis is done with this convention, both for solar neutrinos and atmospheric neutrinos or any other neutrino source. In fact, you will see that Professor Amol Digge will talk about this in the case of supernova neutrinos. Both vacuum and matter propagation is done as in the two-generation case, but are in general more complicated. There may be many other hypotheses for the disappearance of neutrinos like decay and others. At least for some cases you may work out, but it turns out that the oscillation scenario is more robust and fits the observed results far better than any other scenario for many experiments, for almost all the experiments. So what are the open issues? So here is something that we know already from the experiments. Using this realistic three neutrino scenario, the experiments have determined these parameters, the mixing angles and others. So for example, the difference between 1,2 mass, the nu2 mass minus nu1 mass square difference is 0.8 into 10 to the power minus 4 electron volt square. It's a very small number. And in the 3-2 case, we don't know the sign, which is heavier and which is lighter. And this is actually 2.3 now into 10 to the power minus 3 electron volt square. And the sum of all these masses is about 0.7 to 2 electron volts. In fact, this has been made more stringent. The sum is almost less than 1 electron volt. So therefore, you may have almost degenerate hierarchy, or you can have M1 is less than M2, which is much less than M3, allowed by these values, or M3 greater than much less than M1, because this is modulus, which is less than M2. Now this is called as the normal hierarchy, this is called as the inverted hierarchy, and the mixing of nu1, nu2, nu3 and the flavor states is given here. So nu1 is a mixture mainly of electron neutrino, a little bit of muon neutrino, and a little bit of tau neutrino. And nu2 mass eigenstate is a mixture of these three in an almost equal proportion. But nu3 has very little electron neutrino, but mostly muon neutrino and tau neutrino. This is in the normal hierarchy. We can invert it, and this comes below, and these two go up. We don't know what the scenario is, what the ordering of the neutrino masses is, and that is one of the main open problems. So the final slide here. It seems, therefore, the neutrinos, I'm summarizing all the things, the neutrinos do flip-flops or oscillations. It's only when both flip and flop are observed, the agreement with the Bethes theory is obtained. This is possible only if neutrinos have non-zero masses. As you saw, all this oscillation goes away if they have all zero masses as in the standard model. So this is a result away, which is not there in the standard model. Therefore, it's a new thing. It's a window beyond standard model. There's a new mystery. Why do they do these oscillations? Why does theta mixing angles are non-zero? What is the origin of these mixing angles? Is there a fundamental theory which tells you how to calculate them? No one knows. It's an open problem. But there are new and planned experiments which may give more information, like the India-based Neutrino Observatory. There are many other experiments around the world. In fact, Professor Kate Scholberg summarized all those experiments. And in the standard model, of course, as I keep mentioning, neutrinos are massless, they don't mix. So the evidence suggests that the neutrinos are massive, however small that mass is, they mix, and pointing to standard model being incomplete. And you're all young people, you have a lot of work to do, and you need to go beyond the standard model and look at many open problems. So there are many questions. You need new and more precise experiments to go beyond the standard model, This is the neutrino window which has opened, and future can be more exciting when you look at the future through this window. So I have INO briefly, but I will not talk about it. But it is there in the slides. I'll share the slides with everyone so you can read more about INO. And thank you very much. And I have to acknowledge that I have used many figures available in public domain, and also thanks to Amol and Indumati, my colleague, my former colleague, for allowing me to use some of their slides. I didn't even ask them, I just used them. Okay, thank you very much. And questions have already been answered by Professor Vivek Datar in most of the cases. If there are additional questions, you can tell me, or if you want to have something else to ask, please go ahead. Pooja, over to
But
you.
no more questions, sir. There are no questions in the comment box or chat box.
No unanswered questions, you mean.
Yes, sir. No unanswered questions.
Professor Datar has done the
Answered.
answering, and that is a good thing because I told him that he can get 10 more minutes today, but actually I'm giving him only 9 more minutes. So slight approximation there, but I think it's okay.
Yeah.
So thank you very much. Thanks. It was enjoyable talking to you all, even though I cannot see you. I wish I could see you all, maybe next year.
Yes, sir.
We could come back and we could have a meeting where one can see each other's faces.
Yes, sir.
And see the smiling faces at the end of the lectures and not tired faces. Thank you very much.
Yes, sir. Thank you, sir, for this informative session. It was a privilege to have you with us. Now, I request Professor Vivek Dattar to take over the second session. Over to you, sir.
Yeah, thank you. Murthy, could you unshare
Yes,
the slide?
I'm stopping the share. Okay, now you can.
Yeah, okay. Let me go to my slides. Okay. Today, I think what I will do is I'll go to the PDF mode. Perhaps that might be better. Share. Full screen. Okay. So I will start where I left off yesterday. I perhaps went a little slowly yesterday. Um, okay, so I was at this place of Big Bang nucleosynthesis. So these are the few reactions that take place before the the contents of the Big Bang expand and go to low enough temperatures that further nucleosynthesis cannot occur. By the way, in the very early days, Gamow thought that all the nuclei are actually synthesized during the Big Bang. However, very quickly it was realized that that cannot be so, and so these are the reactions that indeed take place. So, I mean, as you can quickly see, that the neutron and proton combine to give you a deuteron. A deuterium nucleus radiatively captures a proton to give you helium-3 and a photon. The two deuterium nuclei can form a tritium and a proton, and also a helium-3 and neutron. These are actually charge symmetric reactions. The helium-3 can capture a neutron to give you hydrogen-3, the tritium, plus a proton. It could also capture it to give you a helium-4. Then the tritium and deuterium can combine to give you a helium-4 and a neutron. This is what is being attempted in Cadranche in France on a very big scale, so that we can possibly produce fusion energy on a realistic scale that we could perhaps then use. Then there is the tritium plus helium going to 7 lithium. It's again a radiative capture reaction. Incidentally, I should just say that those reactions that involve only strongly interacting particles have generally cross sections which are higher than the radiative capture reactions, because the radiative capture involves a photon, which involves the electromagnetic coupling constant, and that's smaller than what is involved in the hadronic interactions. Okay, then the last two reactions mentioned here, the helium-3, helium-4 goes to beryllium-7 and a photon, and then of course the lithium can capture a proton to give you beryllium-8, which quickly decays within 10 to the minus 16 of a second to give you 2 alpha particles. And the beryllium-7 can undergo a charge exchange and so on. So these are the reactions that indeed take place in the Big Bang nucleosynthesis, but you cannot go further because this is so rapidly expanding that so this is one calculation which is mentioned in this review, that as the temperature comes down, as the Big Bang reacting products expand, so this is the time scale starting from 10 to the minus 1 seconds. So you can see that at about 100 to 300 seconds onwards, there is a kind of freeze out, and then the densities of all these nuclei, the number densities of all these nuclei that are formed during this initial part remain the same. That's the so-called freeze out. And so this happens at roughly 3 minutes. And some of you might have read this book by Steven Weinberg. It's a popular book, The First 3 Minutes, and that explains some of these aspects very nicely. Okay, so now, okay, I've somehow missed out on one. Okay, now this is as far as the matter that we know that can interact with electromagnetic radiation is concerned. However, Zwicky had proposed, and Vera Rubin actually in 1970 showed from certain observations that there is a different kind of matter that exists in the universe, and which is about having an abundance about 5 times or so the normal matter. That means the normal matter, I mean neutrons, protons, nuclei, and electrons, and photons. So there is some other kind of matter which interacts gravitationally, but does not interact through the electromagnetic or strong interactions, or the interactions that we know. So the only interaction which it seems to be having is the gravitational interaction. And this was done through the observation of motions of stars in galaxies by Vera Rubin. And so this is actually a seminal piece of work by her. And this is the reference, the original reference, where she looked at stars in the nearby Andromeda nebula, looked at the spectroscopic emissions from there using telescopes that she could access at that time. And such observations, which were refined much later, basically showed that the velocity of these stars as you go out in radius from the center of the galaxy outwards, which should have actually increased according to this dashed line and then come down, go up, but then remain up. In fact, they slightly increase with the distance from the center. So as you go to the outer reaches of the galaxy, the velocities don't come down. And that means that there is a lot of matter in the outer parts of this galaxy. And this you cannot see because you don't see any stars corresponding to that matter. And therefore that came to be then known as dark matter. There is also another thing, since I want to complete this story about astrophysics. The expansion of the universe appears to be accelerating, and this is based on some kind of supernova, which are supposed to be standard candles. And this even fetched a Nobel Prize in 2011. And this, in fact, if you, the canonical interpretation of this is such that this even contributes much more than the dark matter. And if you put all the matter, dark energy, dark matter, and the normal matter that we see in the form of a circle, then about 72% of that is dark energy. Dark matter constitutes about 24%, and the matter that we know constitutes a mere 4%. So what we are talking about is just 4%. The rest of it we know really nothing about. Okay, so this is as far as the introduction to astrophysics goes. Now I'll come back to a brief introduction on nuclear physics. So I start with the experiment of Rutherford, which actually found that there is a nucleus which is of a very compact size inside an atom. And that was done using alpha sources through the alpha scattering experiments. I have a diagram in the next slide, but let me just quickly go through those parts of nuclear physics that are relevant to nuclear astrophysics. The other very important measurement was the one of mass spectrometry of atoms. This was done by Aston originally, and that led to the so-called binding energy curve of nuclei. So the binding energy of nuclei saturates at about a little less than 1% of the nuclear mass. And also, other people contributed to discovering that there are other forms of atoms which have the same atomic number but which have different masses. So they are called isotopes. So this is also important from the point of view of nuclear physics, but also from the point of view of nuclear astrophysics. The neutron was discovered in 1932, and that helps keep a group of protons together through the so-called strong force. So the neutron and proton have interact through strong forces, as also among each other. The neutron and proton also have strong forces, but the Coulomb force keeps on growing as the charge on the nucleus keeps on increasing. So as you go to heavier and heavier nuclei, this keeps increasing, like Z squared by R. That's the potential energy of an object which is roughly spherical and which has a radius of R. So this keeps growing, whereas the nuclear forces are having a very short range of the order of a little more than a Fermi. So that saturates. So if you have very heavy nuclei, then they actually break up through fission because the Coulomb forces become prohibitively large. Nuclei also have, apart from their ground states, they also exist in excited states, and there is, of course, separation energy is involved. You can separate out a neutron. That's called the separation energy of a neutron. You can remove the last proton, the separation energy of the proton, but also other particles like alpha and so on. They are characterized by a spin and a parity. So J pi is what is normally used as a symbol for that. But they are also characterized by another quantum number called the isospin. And so the neutron in nuclear physics, that's the convention you use. You could use a different convention which is actually used in particle physics. Neutron has an isospin of half, the TZ also of half, and the proton has an isospin half, but has a TZ, the projection on the Z axis of minus half. So isospin is also conserved in nuclear processes, except for a small violation due to the Coulomb force. Of course, that increases with as the nucleus becomes heavier and heavier, but then there are other reasons why it still is conserved in heavy nuclei at low excitation ranges. Okay, then there is this so-called strong nucleon potential, which goes, there should have been a minus sign here, there's a typo. It goes down exponentially as a function of R, and R is of the order of 1.4 Fermi. And this is what is actually responsible for binding nucleons in a nucleus, which help overcome the repulsive Coulomb attraction between protons. Also, nuclei, there are stable nuclei which have lifetimes which exceed the lifetime of the universe, and for all practical purposes they are stable. However, there are some which are having very long lifetimes of the order of, let's say, the lifetime of the universe and so on, and then some which are much shorter. So, for instance, uranium has a lifetime of the order of a few billion years, 4.5 billion years. Thorium has a lifetime which is about 10 times longer. On the other hand, there are nuclei which have microsecond half-lives for alpha decay, like polonium 212. So you have this phenomenon of radioactive decay. In fact, that fetched Becquerel and the Marie Curie and Pierre Curie a Nobel Prize long time back in 1903. But there are also decays of the type where a beta particle is emitted, and that was talked about in the lectures of Amol and Murthy, because the beta decay is the one which involves a neutrino as well. So the beta decay of both the positron type and the electron type. So neutron-rich nuclei emit beta minus, and proton-rich nuclei emit beta plus. However, there are some nuclei which can emit both, and that depends on the way the energetics of the nuclei goes, or that particular nucleus goes. If it is having a slightly higher mass than the daughter nuclei corresponding to beta minus emission and beta plus emission, then you can have both kinds of decays. That happens. For instance, potassium 40, that happens. You can also have the electron capture decay, in which the innermost electron usually gets captured by the nucleus and then produces a neutrino and the daughter. So this is a two-body decay as opposed to the three-body decay when you have beta minus or beta plus decay. Of course, you can have corrections to this electron capture, and you can have a photon emission as well, but that's a higher order process that in fact is used by some experiments to measure the mass of the neutrino, or to put bounds on the mass of the neutrino. Okay, then the other processes corresponding to radioactive decay are excited states in nuclei which are below the so-called particle emission threshold. That means below the energy that is required to throw out a neutron or a proton or an alpha. You decay by photon emission, by electromagnetic transitions. Now, electromagnetic transitions can be of the type where a photon is emitted, or you can also have a virtual photon and kick out an electron from the atomic orbital. It could be the K electron, which is the one closest. So that conversion probability is usually the highest. But if energetics does not allow that, if the transition energy is very small, then you can have the L shell electron emission, and that's a process called the conversion electron process. Of course, if you are above the excitation energy where you can kick out a neutron or proton, then that also happens. And you can also have fission decay in very heavy nuclei. You can have both spontaneous fission decay as well as induced decay, and so on. And now this radioactive decay obeys the so-called exponential decay law. And this was also discovered, this very fundamental phenomenon was discovered by Rutherford and Soddy in 1911. And as far as we know, there is no deviation of this exponential decay law in nature. And in fact, this exponential decay law is made use of in dating, for instance, very old rocks, but also dating carbonaceous materials. You might have heard of carbon-14 dating and so on. That's the exponential. Now, this decay law is important because when you synthesize elements, especially in the slow or fast neutron, rapid neutron capture, then you produce nuclei which have decreasing lifetimes, which decay faster and faster as you go along, as you become more and more neutron rich, for instance. And then the decay, the beta decay becomes important, because before it can capture a neutron, it can decay. Okay? So this decay law turns out to be very important in that section of that phenomenon of nucleosynthesis. Okay, so this is just a picture to show you what is Rutherford scattering. All of you might have, or most of you might have seen it. The basic thing that Rutherford found was, when he scattered alpha particles of the gold foil, was that he found large angle scattering. And so the scattering cross section could be calculated. In fact, classically, if you have a charge which is concentrated in a very tiny volume of the order of 10 Fermi or so in gold, and he actually did that calculation and showed that the observation, which were actually carried out by Geiger and Marsden on his direction, they followed this dependence on the scattering angle, 1 by sine 4 theta by 2. And of course, it depended on the charge of the nucleus. So there was more scattering from gold than from aluminum. So he actually studied a variety of targets. This was the start of nuclear physics. Okay, then I come to the binding energy. Now, that binding energy was, of course, is through the measurement of the mass of the nucleus, and very accurate measurements of the mass of the nucleus. What kind of accuracy do you require? You require an accuracy better than 1% of the mass. Okay, so much better than that, of the order of 0.1% or even better. And this was done at the 10 to 100 ppm level in the early days by the first spectrometers of Aston. Of course, he refined them. And this is a kind of generic spectrometer which you have. You have an ion source, you have an electrostatic voltage bending device, and then you have a magnetic device, and then you monitor the current. And when you plot this current as a function of the voltage that you apply here, you can select different masses and you can see different masses. So in fact, if you, for instance, put tin, you will see about 10 such isotopes of tin, right from tin 112 to tin 124. So this, and therefore the peaks in those currents or the area under those peaks correspond to the abundances of those isotopes of that element. If you have, of course, extraneous material, then you see peaks corresponding to those two. Now, this mass spectrometry has been refined over the years, and also the mass spectrometry has been done for nuclei that live for very short times. The mass spectrometer that I showed you before, that can work if you have stable isotopes. But if you have unstable isotopes living for perhaps seconds or even minutes and so on, or hours, then hours probably you can employ that technique, but you have to quickly separate it out and so on. But if it's just for seconds and minutes, then you cannot use that. So this is one example of that. You have these ions stored in a ring. This is an experiment done, for instance, at GSI, but there are other places where such a technique is also used. There's another one in China which does it. And basically what you do is you look at the time information as these circulate around the storage ring. And since you have excellent timing resolution of the pickup coils, then you can, from the orbital time, you can tell what the mass is, because the path is fixed in this ring. So, for instance, you can see that you can get masses of for even unstable nuclei, which are about 1 part in 10 to the 4, 1 part in 10 to the 5. Okay. But the ultimate, of course, is the so-called penning trap. It's an ion trap, which traps atoms for, you can actually, the longest traps have even worked over days and even months. You can trap a single ion and keep looking at it for an extremely long time. But of course, if you have radioactive nuclei, then you can only look at it for the time till it decays. And this has been used. Basically, the method is that if you have a magnetic field, then any charged particle has a so-called cyclotron frequency, which is just given by QB by M. And at very low energies, there's no relativistic increase, so you have a very sharp frequency. And you can store these ions by putting a quadrupole field here. So you have a voltage plus V and plus V here, so the ion gets trapped between these electrodes. But it also cannot go in the lateral directions because there is a magnetic field, and it has to be within this trap. And by determining this cyclotron frequency, you can actually measure very accurately the mass. For short-lived ions or for short-lived nuclei, you can determine this to about 1 part in 10 to the 8. But for longer lived things where you can make the observation repeatedly, then this even comes down to about 10 to the minus 10 or 10 to the minus 11. Now imagine if you have a mass 100 nucleus, the order of the mass of a nucleon is about 1 GeV. So you have 100 GeV. So the 100 GeV is about 10 to the 11 electron volts. So which means that if you have a sensitivity for a stable nucleus, delta M by M of the order of 10 to the minus 11, then you can get it down to about 1 electron volt. So if you have, for instance, isomeric excited states of this nucleus, you can determine even those isomeric states, the masses of those isomeric states, and take the difference, and you can tell what is the energy difference. This is really fantastic. This is a fantastic development over the last 10, 15 years, actually 20 years or so. So with such accurate mass determinations, of course, you can get a binding energy. What is shown here is at a much coarser level, because that is usually enough for many purposes. So what is shown here is the binding energy per nucleon. So you take the total binding energy, which you get from the mass, because from the mass, then you can subtract what is the mass of the individual neutrons and protons, and then you get the binding energy, and then you divide it by the mass number, and you get the binding energy per nucleon. And this turns out to rise for low masses. So the deuteron, for instance, would be way below this. It's not even, the scale is already a shifted scale. So As you know, the binding energy of the deuteron is just 2 MeV, so the binding energy per nucleon is 1 MeV, way down. So then helium-3, but by the time you come to helium-4, you are actually somewhere here, somewhere in the graph. That's about 7 MeV per nucleon. And then when you go higher and higher, it sort of saturates at about iron. So that is what Amol said, that the most stable configuration of nuclei, or the nuclei with the largest binding energy per nucleon, are nuclei near iron and nickel. And then when you go higher and higher, then what happens is that the binding energy comes down, because now you have saturated all the nuclear two-body interaction that you can have, because somebody who is very deep inside the nucleus doesn't actually see nuclear interaction, nuclear force between somebody who is about 7-8 Fermi away, okay, or sees at least a weak, relatively weak force. So as the nucleus grows in size, as you keep increasing the Z and hence the A, two things happen. Because of the Coulomb force, you actually you have to put more neutrons than protons in the nucleus to keep it stable, number one. Number two, and since the Coulomb interaction grows like Z squared, whereas the binding energy after saturation goes only as A, then this binding energy decreases. Okay. So for instance, by the time you are at about uranium, this binding energy is only 7.5 MeV per nucleon. So in fact, this binding energy was put to use by Lise Meitner to explain fission decay, and the fact that about 200 MeV is given up when heavy nucleus like uranium-235 fissions. You can even estimate what that energy is, because if you have two fragments of about mass 120 or so, then you get about 0.7 or 0.8 increase in binding energy is released in the form of kinetic energy of the fragments. So mass is basically converted to energy in the form of kinetic energy of the fragments. But this is also useful, as I said, from the point of view of fusion. So when you are somewhere in this region, you can fuse two nuclei to get to a higher binding, and therefore you can make heavier and heavier atoms till you reach iron or nickel. But after that, if you fuse iron with, let's say, alpha particle or a carbon nucleus, you have lesser binding energy. So the Q value is negative, and since the temperature is not that high in terms of keV or meV, so you cannot then populate, you cannot make these elements through the fusion reaction. That's where the neutron comes in, as we will see. Okay, so typically the binding energy is of the order of 8 MeV per nucleon, which is a little less than 1% of the nucleon mass, if you given the mass energy equivalence. Okay, now let's come to the reactions. At very low energies, which is relevant to stars, and this is energy per nucleon of, in fact, much less than 1 MeV, nuclear collisions are dominated by elastic and inelastic scattering, as the case may be, but also by fusion, radiative capture, and some amount of transfer reactions. At stellar energies, these charged particle reactions, of course, involve tunneling, because suppose you have a temperature of typically a few keV, then the barrier, even for P plus P, is of the order of an MeV. So you are way below the barrier. I think I should show you a figure here. So if you look at this figure, as two nuclei come together, so as R decreases, you first face the Coulomb barrier, and then beyond a certain distance of approach, then you start feeling the nuclear potential. But if your energy is so low, somewhere here, this is a measure of the energy on the y-axis. There's a potential, of course, here. But if your energy is very low, then classically you cannot actually approach the nucleus, okay? And you cannot therefore make a nuclear reactions. But what quantum mechanics tells us, and this sort of calculation was first done by Gamow in the context of spontaneous alpha decay, where you have just the reverse. You have an alpha which might be formed for a very short time in the nucleus, that's somewhere here, a few MeV, and the barrier for these heavy nuclei is of the order of 20 MeV, so way below the barrier. But it can come out because quantum mechanics tells us that you can tunnel through this barrier, and that's how you get alpha decay. And nuclear reactions well below the barrier are in fact just the reverse of that. You come in with a low energy, you tunnel through the barrier, and you make the nuclear reaction. You can make a fusion reaction, you can have a radiative capture, and so forth. Okay, so let me go back to this. So at stellar energies, you do need tunneling, a quantum mechanical phenomena. When it leads to combining of these nuclei, you can form in principle a compound nucleus. And this compound nucleus is characterized by some quantum numbers like energy, angular momentum, and the parity, and so on. But the decay, most importantly, the decay is independent of the way it was formed. As I said already, nuclear fission is important in heavy nuclei. So when you want to, say, synthesize nuclei, if you can't synthesize arbitrarily heavy nuclei, at some point nuclear fission will start coming in, and these heavy nuclei will decay through nuclear fission. The other processes that are important are the giant electric dipole resonance. So this is a phenomena where if you shine a nuclei with the photon beam and you start varying this photon beam energy, then you find a very broad resonance occurring at about 15 MeV or so in medium and heavy mass nuclei. Of course, it varies with the mass number, but the cross section shows a very generic peak, and that's called the giant dipole resonance, because basically when this photon interacts with the nucleus, the neutrons and protons vibrate against each other collectively, and so that's why it's called the giant resonance. But there can also be spin isospin resonances, and they are important, for instance, in beta delayed neutron emissions, which can take place, for instance, when you synthesize neutron rich nuclei in stars. The other thing to remember is that the nucleons in a nucleus move in an average nuclear potential, which could be spherical or deformed. So some of these nuclei could be spherical when they are close to so-called magic numbers, but when they are away from magic numbers or in between a set of two magic numbers, then they can be deformed. And when they are deformed, of course, they can exhibit rotational motion. And nuclei, of course, can be described. Many of the nuclear properties exhibit a smooth behavior with A, but there are shell corrections near the so-called magic numbers. So these things have been studied and so on over the years. Okay, as I said, nuclear collisions at low energies exhibit a variety of processes. And let me go to the next slide. Yeah. So this shows, for instance, as a function of impact parameter, which is quite a useful concept when you are at low energies, because then the de Broglie wavelength is fairly large, and you don't really approach the nucleus too close. So you can actually define, you can have a semi-classical description of the process of scattering and even of reactions that has been done. So let me go over to this. So as you increase the impact parameter, large impact parameters, for instance, you only have elastic scattering, and mainly this is dominated by Coulomb scattering. As you come a little closer, the Coulomb force can also excite states both in the target and projectile. If you come still closer, you can have radiative capture. Means you can have, for instance, if you have a proton or alpha particle, it can get captured and can emit a photon. You can also have, in a similar domain of impact parameters, when you are sufficiently close to the nucleus, when there is just some small overlap between the wave functions of the target and projectile, then you can have transfer and pickup reactions. For instance, PD reactions, where you pick up a neutron from the target nucleus, or of course it could also be vice versa if you have a heavy impinging on a light target. Or you can have DP, this is called the stripping reaction. You can have elastic scattering through the Coulomb or the nuclear forces. And of course, if you go very deep inside, then this happens. By the way, I should have actually cut this out. This is a slide that I borrowed from some other slide that I had made. This actually doesn't happen at very low energies. And when at the small impact parameters, of course, through tunneling process, you can have a fusion reaction, which leads to a compound nucleus. And then that compound nucleus decays depending on the quantum numbers that it has. It's independent of the way it was produced. So if you produce the same compound nucleus using A1, A2, but A1 prime, A2 prime, and they populate the same, they have the same quantum numbers of the compound nucleus, then that decay is independent of how it was formed. Okay, this I have already shown. Now, the fact that the radius of the nucleus, at least the charge radius of the nucleus, goes like A to the 1/3, was shown in electron scattering experiments of in the 50s by Hofstadter and company. So they scattered electrons of nuclei, and they found this relationship between the charge radius of the nucleus and A. So where the relation was approximately R0 a to the 1/3, where R0 is of the order of 1.2 Fermi. Now, this probes the charge radius. If you do a similar thing with hadrons as projectiles, then you get the so-called nuclear matter distribution. And it turns out that for stable nuclei, the charge radius and the hadronic radius are roughly the same. Okay, this I just mentioned because in some peculiar situations, this could be important. If you smash two nuclei at extremely large energies, relativistic energies of the order of 100 GeV per nucleon or even higher, then you can actually produce something called the quark-gluon plasma. So we know that in the interior of nucleons, neutrons and protons, for instance, you have quarks, but you also have gluons, and they move more or less freely inside of the nucleon. But if you can create a situation where you have nucleus such as gold, which is at a very high temperature, then temperature of 100 or more MeV, then you can have quarks which break away from the nucleons and which can travel all over the nucleus. And we believe that we have already produced such a state of matter, so-called quark-gluon plasma, in collisions at RIC and the LHC. And this kind of plasma state may, in fact, be relevant to the interior of stars, neutron stars, when these explosions take place, supernova explosions take place. Okay. Now, I come to nuclear reactions with neutrons. As I said, charged particles can make reactions with nuclei, and indeed do. However, they face the Coulomb barrier. So, on the other hand, the neutron has no electric charge, and it only has the strong interaction. And so it can react with the target nucleus at very low energies, at thermal energies, and with the heaviest of nuclei, because it doesn't care about the charge. The reaction cross-section, at least the smooth part of this reaction cross-section at low energies, is approximately given by pi times R, where R is the radius of the nucleus, of that heavy nucleus, plus reduced de Broglie wavelength of the neutron. So if the neutron wavelength is large, as happens when the neutron has low energies, then this cross-section is fairly large. Now, this is as far as the smooth part goes. But sometimes you can have so-called resonances. At very low energy or even at higher energies, you can have resonances where the cross-section can be so large as, I mean, in some nuclei, for instance, like gadolinium, this cross-section can be of the order of a fraction of a million of a barn, 250,000 barns. Okay? So these were first studied by Bright and Wigner. They had been observed, or hints of that had been observed by experimentalists before that. And Bright and Wigner gave the theory for that. So you have the so-called Bright-Wigner resonance. So the scattering amplitude basically has a smoothly varying amplitude and a resonant amplitude. And I'll show a picture later from experiments which show these resonances. Okay, so this I should quickly go over. This is a very seminal paper of Niels Bohr as to a mechanical model of the compound nuclear formation. So he shows a billiard ball interacting with balls in a depressed bowl, and then when this comes in, it shares its energy with the balls in that bowl. But once in a way, one of them gets enough energy to come out of the ball. Okay, and that takes a very long time. So the compound nucleus, this is what he wanted to show, that a compound nucleus can live for a long time, and therefore it has you can have very sharp states at relatively high excitation energies of around 8 MeV or so. Okay, so this is the same thing, that if you have a nucleus, you keep exciting it, there are discrete states, and then you come to the so-called particle emission threshold. Usually that's a neutron, which is at around 8 MeV or so. But if you go above that, the density of states starts increasing, and you can also have very sharp. I mean, there might be several levels within electron volts of each other, and if the neutron comes in with just the right energy, then you can hit a resonance. So you can form a compound nucleus of just the right energy, and when you slightly increase the energy, then you're off resonance. So the cross section drops dramatically. Then again, as the energy increases, you can hit the next resonance, and so on. Till a point when you go up in excitation so much that these levels start overlapping. And then again, because then the things average out, and then you see a relatively smooth behavior of the cross section. But in this domain, very close to the binding energy of the neutron, just above it, you can observe very sharp resonances. And these can be studied experimentally. So, for instance, there is this time of flight experiment, the so-called NTOF experiment for studying neutron cross sections at the CERN proton synchrotron. So there, what is done is you take a very high energy proton of the order of 20 GeV, smash it against a very thick target of, let's say, carbon or so, and then you produce a large number of neutrons. Every proton of this 20 GeV can produce about 300 neutrons or so. Okay, and if you there are tricks in which you can, in a synchrotron, you can take out the beam in one go. Okay, so in about a few nanoseconds, you can push that beam, all of it, which is the average circulating beam might be of the order of microamperes or so. All of that can go onto a target, and within about a few nanoseconds, you get a burst of neutrons. Then around this target, you can put a moderator, something that, but not a full moderator, a partial moderator. So it can thermalize some of these neutrons. So it basically, from very high energies, you can bring some of these neutrons down to very low energies. So that's shown in the next slide. And then what you do is, since this is all coming out in a very short time, you can go and set up your experiment where you want to measure the neutron cross sections, be they fission cross sections or capture cross sections or even elastic scattering cross sections and so on, very far away from this. So the length over which these travel actually give you energy resolution, at least for the higher energies. For the lower energies, the energy resolution is determined not by so much by the flight path, is determined by the size of the thermalizing material that you have. So anyway, so if you do that, you put a partial amount of moderator around the target. So what is shown here is normal water, borated water, and some other way of moderating it. Then you can see that you get a wide spectrum from this is plotted in terms of electron volts. So this is like 1 MeV, and this is 10 MeV to about a fraction of a electron volt, milli-electron volts. Okay. This was actually proposed by Carlo Rubbia, who found experimental evidence for the W and Z bosons. He had this very beautiful proposal where you could measure these cross sections just in one go. Before that, these cross sections used to be measured by time of flight facilities, which had access to a certain band of energies of neutrons. And even before that, actually, Fermi was the first one to do such experiments using a chop beam from a reactor. So you had two choppers, and depending on the phase of these choppers, these two choppers, you could select a certain velocity neutron. But then this was a kind of experiment which only looked at a narrow band in energy, and then you had to increase the velocity of the angular velocity of these choppers in order to go to higher energies. So one energy band at a time you have to do. But this experiment, for instance, is very powerful because it can take right from milli-electron volts to tens or even 100 mega electron volts in one go. Okay, so this is a figure which shows the total cross section in this case of as a function of neutron energy. As I said, in one go this can do it for a variety of targets. So you can change these targets, and these cross sections can be measured. Now you can see that for the light nuclei, you have very sharp peaks appearing at certain energies. These are these Breit-Wigner resonances, but they are fewer in number. Okay, as you go to heavier and heavier nuclei, you get many more resonances, a denser population of these resonances. So these resonances are important. For instance, in reactors, nuclear reactors, you have to know what the cross section is as a function of energy. So especially so for the fuel, which could be U-235, or it could be plutonium, or it could be something else, U-233, and so on. And you need to know how these neutrons interact with the fuel. uh, of course, what you need is not just the total cross section, you also need the fission cross sections, which have also been measured. I just gave you a sample of this. And also for the materials that constitute the reactor, meaning the so-called calandria where this fuel is housed and so on. So this is a way you can measure. But this is also extremely useful for astrophysics, nuclear astrophysics. So you can in fact stick in a stable target, whose cross section you would like to use in your nuclear astrophysics scenario, or you could even put a radioactive target, and I mean it can be our half-life target. You can do some radiochemistry and put it in here, because this in one go measures the complete cross section over a wide range of energy. And of course, what is relevant for astrophysics is probably in the region of up to about an MeV or so. Okay, so this is as far as the introduction to nuclear physics goes. I think if there are any questions at this stage, you may please ask. I don't, let me see, I don't have the chat here. So can the organizers tell me if there are any questions? Otherwise, I will move to the next, what I had planned as lecture 2.
So Vivek, you can proceed.
Okay, there's no question? Okay. Okay, so I unshare this. Say, first of all, I have to go and open the second file, fusion reactions. Okay, then I say a new share. And let me see. I can see it here. So I think it is this one. Yeah, this is the one. Okay, so view full screen mode. Okay. So in this part, I intend to talk to you about the fusion reactions that occur in the sun. You have already seen these reactions in, I think, in Murthy's talk. So the first part I had prepared, but I will skip that. Or maybe I could just remind you very quickly. What are the fusion reactions that take place in the sun, and what is the evidence that we have that these reactions take place in the sun? Okay. And also, I will tell you about measurements of nuclear properties and reactions of astrophysical interest. Now that, I guess, it's 10 minutes past 6. So maybe I have about 45 minutes for this. I may not be able to cover much of this, but maybe I will be able to start on this and then take it to the next lecture. Okay, so this has already been said, but just to remind you that Helmholtz, Lord Kelvin, and so on estimated the age to be 30 million years based on gravitational energy released during contraction of the sun. But of course, they did not know about this new source of energy, which is the energy due to fusion of nuclei. And also, this was in conflict, as Murthy pointed out, with the Darwin's theory of evolution of life on Earth, and that required at least a few hundred million years or a few giga years, billion years. And Rutherford already showed using radioactivity, using the radioactivity of uranium, that the Earth is about 4.5 billion years ago. And if the Earth is about 4.5 billion years ago, the Sun has to be equally, if not more, older than this, 4.5 billion years. So Eddington quickly realized that nuclear processes have the potential of powering the cores of stars, and the Sun is one such star. And so if you combine 4 protons, and we'll come to the reactions, it's not that 4 protons actually combine in one go and produce a helium-4, but they go through a series of reactions. But essentially, if you boil down this, you have an energy release when 4 protons get converted ultimately to 4 helium, an energy which is the order of 20 MeV or so. And this is enough to power the sun, because this is a much more powerful source of energy. Okay, so Bethe in 1939 proposed these nuclear reactions as powering the sun. Bethe was the master of nuclear physics in those days. Everybody actually referred to the Bethe Bible. He had 2 review articles in the Reviews of Modern Physics, which basically said all that we know about nuclear physics at that time. So he was aware of all that was there to know about nuclei, and he proposed the carbon nitrogen oxygen cycle as being the one responsible for producing this energy in the sun. Of course, he quickly realized, actually in that first paper, he said that the PP is very unlikely to produce it because the first reaction is a weak interaction. It goes through the weak interaction process. So that's why we had proposed the CNO. But then the question is, where do you get the CNO from? So in the next paper, he actually proposed that no, it's the PP cycle that is at least contributing an equal proportion to the energy production in the sun, and perhaps CNO is producing only half the energy. So from PP not contributing or contributing insignificantly, he came to this conclusion in the second paper that it's PP that is equally important, if not more, in the sun. Okay, so this is the same thing that was shown that Eddington proposed that fusion nuclear processes contribute. So I will not dwell on this. So let's quickly come to the PP and the CNO chain fusion reactions. So these are two chains, PP chain and the CNO chain of fusion reactions. Okay, so in the PP chain, the very first reaction, and I've colored that in blue, this PP chain accounts for about 99.8% of the reactions, including the ones that follow. But the very first reaction is the P plus P going to deuterium nucleus, a positron, and a neutrino of the electron type. The so-called Q value, which means the mass difference between the initial state and the final state, is 0.42 MeV. So this, since it's a three-body decay, and since the deuterium is much heavier than the positron and the neutrino, this is basically shared by the positron and the electron type of neutrino. So the neutrino that comes out basically has an endpoint of about 420 kilovolt, 420 keV, and starting from, of course, zero energy. So it peaks at around something like 150, 200 keV, the neutrino energy spectrum. But most importantly, I'd like to emphasize that this is a weak process. A weak process means that this reaction cross-section is extremely tiny. And were it not so tiny, were it, for instance, to go through some kind of electromagnetic process, then the sun would have died in a matter of days. Okay? The fact that it lives for billions of years and expected to live for another quite a few billion years is due to the fact that there's the neutrino involved in this very first reaction. So it's a kind of very slowly burning process. Just like you have these slowly absorbed medicines, this is a very slowly burning nuclear process that is powering the sun. However, the sun is pretty powerful, as we know. It gets pretty hot during the day, and that is because, of course, the sun is huge. And so even if this reaction cross-section is so tiny, the number of these reactions is so large that, what was that number? I forget that number. 2 into 10 to the power of 30 joules per second, I think, is the total energy emitted by the sun. That's the luminosity. Or unless I've got it wrong, it's ergs and not joules. But in any case, it's a huge amount of power that is radiated by the sun from its surface. And all that is happening because of this set of nuclear reactions. So the weak interaction is crucial to the sun, both by way of initiating the PP chain, but also the fact to keep it burning for so long, okay, for billions of years. Okay, then having made a deuteron, then of course it can combine with a proton through a so-called radiative capture reaction. As I already said, all these charged particle reactions undergo the tunneling process. The sun, even in its core, the central core temperature is about 15 million degrees centigrade. So if you work that out, that works out to be about 1.3 keV. And the proton-proton Coulomb barrier is of the order of an MeV. Okay, so it's really way, way below the Coulomb barrier, and quantum mechanics comes to our rescue. So you have tunneling, which makes this reaction go through, and then of course the weak interaction to make it even further slower. Okay, so the PD gives rise to helium-3. This is a higher Q value reaction, which means more energy is released in the form of the photon. And then helium-3 combines to form helium-4 plus 2p. By the way, this is a very nice example of sort of green reaction. However, we would find it rather hard to reproduce this in the man-made reactors, fusion reactors, because this has a charge of 2, this has a charge of 2, and the Coulomb barrier has increased as compared to the dt by a factor of 4. But nevertheless, this is an example of a very clean reaction in which the final state has only charged particles and no neutrons at all. The dt, in fact, produces a neutron in one of the channels. That's the only channel. dt goes to helium-4 plus n. It's a 14.4 million. Okay, so this is an example of a all charged particle reaction, and this cross section has been measured, in fact, at the energy that it is required. Okay, then there is the pp2 chain, which means you go further down. The helium-3 can combine with helium-4 and produce a beryllium-7. Beryllium-7 is a radioactive nucleus with a half-life of the order of tens of days. And then that can capture an electron. It actually decays by electron capture. So the innermost shell electron, the K electron, actually gets captured by the beryllium-7. However, in the sun, at the high temperatures that you have, all the K shell electrons are actually unbound, or most of them are unbound. Very, very small probability that there is a K shell electron. Because the interior of the sun is basically a plasma. Okay? So you have continuum electrons that can get captured by the beryllium-7. So the continuum electrons, of course, have a probability that they have L equal to 0. So you can decompose it into various partial waves. And the S wave part, of course, contributes to the electron capture. Okay. So this produces a monoenergetic neutrino, as opposed to this, which is a continuous spectrum from 0 to 420 keV. This produces a monoenergetic neutrino of 860 keV or so. Then you can have lithium-7 plus proton going to beryllium-8. And as I said, beryllium-8 lives for a very short time, of the order of 10 to the minus 16 seconds, which is long on the strong interaction time scale, but short from the practical viewpoint. And then it decays into 2 alpha particles. The pp3 chain, in this figure, I have not put the branchings or ratios and so on. That there is another figure following that. I thought this would get cluttered up too much, so I only put in a few numbers here. The pp3 chain, you have helium-3, helium-4 going to beryllium-7, but then followed by beryllium-7 plus proton going to boron-8. So this is the so-called 1,7 reaction, producing a photon, and then the 8 boron can decay to beryllium-8 and a positron and a neutrino. Now this has a very large positive Q value decay process. So the energy released in this is of the order of 18 MeV or so. So again, because the beryllium-8 nucleus is a very heavy nucleus, this energy is shared between the positron and the neutrino. So you have a neutrino spectrum going all the way from 0 energy to 18 MeV, but peaking at around something like half that number. Then, of course, beryllium-8 quickly decays into 2 alpha particles. There is a very small pp4 chain, which is that helium-3 can actually combine with a proton, give you helium-4 and a positron and a neutrino. Sorry. Next slide. So this is again a weak process. So just like this, it is, it has a very small probability of occurring in the sun. That's why it is only 0.2 ppm. It's much smaller than this, of course, because of the higher Coulomb barrier. Helium-3 has 2 protons. So as compared to this, the barrier is increased by a factor of 2. And therefore, this reaction is even weaker than the P plus P reaction. This has, of course, a very high Q value because helium-4 is very tightly bound. Helium-3 is not so. And therefore, you can get a Q value which is rather high, of the order of about 90 MeV. But this, I think, even the next generation of experiments will find this hard to measure. Then there are the so-called PEP neutrinos, in which, because this is a plasma, the electrons can combine with the 2 protons, which happen to be close by, and then they can form a deuterium and a neutrino. Okay? This is again a weak process, but because the charge of the proton is less than the helium-3 by a factor of 2. So then this sort of competes with the P plus P. So the advantage here is that you have a monoenergetic neutrino. Of course, it's a low energy neutrino, uh, but it occurs for not too small a fraction of the time. And this actually it may be possible to measure it with suitable detectors, which have good, for instance, one of the things could be that if you have a good energy resolution, you can make out this neutrino energy in the form of a peak in that spectrum that you measure. It's a low energy neutrino, so it is, of course, has the same problems as measuring low energy PP neutrinos or beryllium-7 neutrinos and so on. But at least it is a peak. So just like the beryllium-7 neutrino, which is a peak because of the electron capture decay, similarly here you have a two-body decay and therefore you have a peak. Okay, so these are the reactions in the PP chain. This is again shown here, again in a slightly different way. So you have this chain with 99.76%, but once you get here, then there are two branches, or actually three, but this is a very tiny branch, as I said. This is 83% and then 16.7%. One part going to helium-3, and the other helium-3 plus helium-4, which goes to beryllium-7 gamma here, or charged particles. Then you have this fraction of the reaction chain going into beryllium-7 electron capture, and a much smaller fraction going into proton capture, so which produces boron-8. But as I said, this boron-8 produces the highest energy neutrinos, and they are somewhat easier to detect by certain kinds of detectors. So, for instance, the Davis and the Kamioka experiment, which Murthy talked about, and also I think Amol, but maybe Murthy more, is that these are the neutrinos that are measured. But you can see that this is a very small fraction. Okay, this is only 10 to the minus 3 of this. So, so 0.6 multiplied by this. So this is like 1 part in 10 to the 4 of that order. Only those many contribute to the boron-8 neutrinos. But since at low energies the neutrino cross sections go like E squared, this is not to be this actually can be measured and has indeed been measured to good effect. And then, of course, this boron-8, this is the three-body decay shown here. Whereas in this case, you get beryllium-8, which then quickly decays into 2 alpha particles. Okay, so then this is the CNO chain. So it was believed by Bethe initially that the CNO chain is quite important. As it turns out, now we have measurements to show that it's a very tiny fraction of the PP chain of reactions. So it goes like this. If you have carbon, then it can capture a proton, and via radiative capture produce 13 nitrogen. Then this beta decays because the stable isotopes of nitrogen are 14 nitrogen and 15 nitrogen. So this is a relatively proton-rich nucleus. It decays undergoing positron decay, of course, emitting the corresponding neutrino as well. So it's a three-body decay. Then goes to carbon-13, which can capture a proton to form 14 nitrogen. Now, 14 nitrogen itself is stable, but in the environment in which there are protons, it can, of course, undergo radiative capture. It can produce 15 oxygen. Then can, through beta decay, so the oxygen isotopes that you know, for instance, oxygen has 3 stable isotopes, 16, 17, and 18. And 15 oxygen is radioactive. And it can decay by beta plus emission and a neutrino, of course. And then it goes to 15 nitrogen. Now, this 15 nitrogen has 2 pathways. It can undergo a P alpha reaction. So it reacts with the proton, but emits an alpha to produce a carbon-12. This is one path. The other is radiative capture. And this, of course, goes to oxygen-16. Then the oxygen-16 goes through P gamma radiative capture to 17 fluorine, but 17 fluorine is radioactive. The only stable isotope of fluorine is 19 fluorine. So this is unstable. So is 18 fluorine, because 18 fluorine is used in PET tomography. But the 17 fluorine, which is produced in stars, that decays to oxygen-17, which in turn can react with the proton through the P alpha reaction, go to nitrogen-14, and then this cycle can again continue in both these directions. So one cycle goes like this, the other cycle goes like this, and these are the 2 cycles that can occur. So this is called the CNO cycle. So this is the reference. This figure is actually taken from Reviews of Modern Physics article. Okay, this is again a similar depiction, except that even weaker chains now are shown. Of course, weaker chains in terms of the sun, but in heavier stars, you can go further. And for instance, apart from this PP chain, the CNO chain, you can also have through the P gamma reaction 18 fluorine produced. Then you can go to oxygen 18, fluorine 19. You can go to P gamma to neon 20. Here you can go through decay to 18 neon, and so on, and this can continue. So in hotter and hotter stars, you can have further captures of protons beyond just CNO. Okay, so let me come back to this and then go on to neutrinos. But before I do that, let me just say that the first proposal for these set of reactions actually was by Weizsäcker. So Weizsäcker actually did it a year before Bethe. He proposed the PP and the CNO reactions in two papers in 37 and 38. But Bethe and Critchfield in 1938 proposed that this reaction in the sun was estimated, and it was estimated to be very small. So in the first paper of Bethe, the CNO cycle was proposed, as I've already said. And this was supposed to be the main source of energy production. In the second paper, he proposed this. And interestingly, he didn't put the neutrino there. Okay, so the neutrino is absent in this equation. So you can see that, for instance, angular momentum conservation is violated. Not that Bethe did not know of that, but I think he just avoided putting the neutrino because he thought that this has not been yet found and is very unlikely to be found. So he didn't put it there. But he must have been aware that this violates conservation of angular momentum. Is also at that time, I don't know whether the electron number conservation was known, but in any case, angular momentum conservation is not obeyed in this. So, so he somehow just did not put it. Now, the next important phase in this came about when Bruno Pontecorvo first proposed detection of neutrinos by a radiochemical method. And this radiochemical method, so actually there is a report which is a Chalk River report. He was in Canada at that time in 1946 when he wrote this. The neutrino can interact with chlorine 37, produce an electron and 37 argon. Now 37 argon is a radioactive nucleus. It has a half-life of about 35 odd days, and if you produce it over a month or 2 months, then you can, if you can extract this radioactive argon and count it, then you have basically integrated the flux of neutrinos over your detector for a period of about a month or 2 months. Now, Louis Alvarez is also a Nobel laureate for measuring lots of nucleon resonances and other hadrons using bubble chambers in Berkeley, Lawrence Berkeley lab. He proposed using sodium chloride. By the way, let me see, I should minimize this. Sorry. He proposed using the CCl4, that means carbon tetrachloride, which contains chlorine. And then, of course, it has both isotopes of chlorine 35 and 37, but about 1/4 of the total amount of chlorine is in the form of 37 chlorine. So he proposed that you somehow or the other manage to extract 37 argon. Alvarez said that you can do this by putting sodium chloride, which is a more innocuous material than the organic fluid. But he also proposed something else. This is, I'm coming before this time. Let me just go back. What he proposed was that you can actually flush out this argon by putting a rare gas. I think in the original proposal of Alvarez, actually he didn't follow it up with an experiment, but he just proposed in some maybe personal communication or something with his colleagues that you could actually flush it out with helium, for instance. And then the rare gas of argon would come out along with it, and then you could put it into a counter and count it in a low background environment. This idea was actually taken up by Davis and Bacall, as we will see. But before I come to that, let me just go back to the proposal of Pontecorvo, where he repeats the dimensional arguments of Bethe and Piles to estimate an upper bound for the neutrino nucleus cross section, and where actually Bethe and Piles had concluded in that Nature paper of I think 34 or something like that, that there is no practically possible way of observing the neutrino. And the argument that they used was basically dimensional. You produce a cross section with a quantity which is like L squared times T, and use the physics is actually in this tau, which goes like T, which is corresponding to the lifetime of a beta decaying nucleus. So you construct H cross by P nu, that is the dimensions of L squared, and this T is produced by H cross by P nu C, and then divided by tau, which is the dimensions of time. And if you use 5 MeV 0.1 second for a beta decaying half-life, then you get these numbers, and you actually get a rough order of magnitude of 10 to the minus 42, which Bethe and Pyle said is impossible to measure. In fact, you also get the E dependence at very low energies through this interaction, so-called what we call now the charge current interaction. At low energies, this factor goes like 1 by E squared of nu, 1 by E of nu, and then the tau goes like inverse of E nu to the 5, because it's a three-body decay. And then you get an E nu squared dependence. So Pontecorvo concluded that if you take the solar neutrino flux, then it would be very difficult to detect these solar neutrinos with a 1 meter cube detector of CCl4s. So he, in fact, concluded that maybe a reactor or an accelerator environment would be better for detecting neutrinos. This might be more promising, because in an accelerator environment, perhaps you can get higher energies of neutrinos where the cross section goes like E squared, or in a reactor where the flux is very large. In fact, a gigawatt thermal nuclear reactor produces about a few times 10 to the 2 times 10 to the 20 neutrinos per second. So if you are at close distances from the core, you can possibly get high fluxes of neutrinos. So he concluded that this is not possible. Of course, part of this conclusion was based on the fluxes of neutrinos known at that time. And so Bacall and Davis actually took up this idea. I remember having seen some article where they are even supposed to have actually asked Pontecorvo if he wanted to follow up on his idea of the radiochemical neutrino detector. And he apparently said, no, I'm not intending to follow it up. And so therefore, and it was those days, in which, I mean, there was not such hectic competition, perhaps. And they actually asked Pontecorvo, he said no. And then they proceeded to put up a proposal to Brookhaven National Lab for making such a detector. Of course, initially, Davis decided to do this experiment at a reactor, and indeed he found a negative result showing that neutrinos and antineutrinos are different, because what comes out from a nuclear reactor is antineutrinos, and what comes out from the sun is neutrinos. So he didn't find any signal when he put this radiochemical, a relatively small radiochemical detector at near the reactor. He didn't find a signal and concluded that antineutrinos are different from neutrinos. He also decided to use the safer C2Cl4, which is a cleaning fluid and less problematic than carbon tetrachloride. We now know that, of course, carbon tetrachloride is can cause cancer and so on. Anyway, so he borrowed Alvarez's idea of using inert gas to flush out 37 argon, radioactive argon, but he did it now with argon gas itself. So if you take pure argon gas, you can put it, bubble it through the tank of C2Cl4 and then flush it out. And then the small amount that you have put in, you take it out and then count it in a very low background setup. In fact, this low background setup was using some big gun, I think, of heavy metal, which he found as a surplus after the war, and that provided very good shielding from the outside radioactivity. He also had to build a relatively large detector, as Murthy pointed out, in order to get a decent count rate. And he had to build, for instance, 600 tons detector of this material, and also put it up in a deep mine, which fortunately the operators of this mine agreed to have a cavern which suited him, and that had a depth of 1.5 kilometers. So it was quite away from any other sources of cosmic muons and so on, which might produce this radioactivity of argon 37. So at this depth, actually, the muon flux goes down by, I think, about a factor of 10 to 100 million. So here is shown Ray Davis and John Bacall, who made the original proposal. This is, I think, Bacall inside a tank where you flush gas. So this initially, this flushing process was done with not with radioactive material, but with just normal material to see how much of the efficiency, how much gas you put in, how much you can get out through the purifiers and so on. And this was the ultimate tank that was used, and this is Ray Davis. So this is from a talk of Ray Davis in 1971, where he showed the rate at which these neutrino interactions take place. I'm sorry, there is no scale here. It should have been so many reactions per unit detector volume. This was the theory in those days, the CNO and the PP cycles, and this was what he had got a bound from the reactor experiment. And these two started to meet at some point. Otherwise, theory was saying that there's too few neutrinos, and this was becoming a little difficult to detect. But finally, theory and experiment came together, and that's when Davis got going. Bacall had a very seminal contribution to make in this whole business. He was not an experimentalist; he was a theorist, but he stuck to the task of actually calculating what the sun should produce in terms of neutrinos. So, of course, this is a spectrum from a much later date, from 2005. He had been at it since the 60s and continually refining the calculations. So, in 2005, for instance, from a paper of his, this is the flux of neutrinos in number per square centimeter per second. So, this is the PP neutrinos. By far, they are the dominant ones, but they are, of course, much harder to detect than the boron 8 neutrinos, which are much smaller in numbers by a factor of about 10 to the 4 or so. But because of this E² dependence, and also because of the fact that they have high energies and they come above the thresholds where you're bothered by radioactive decays and so on in a detector, so they become relatively easier to detect. So this is the spectrum that is gives you an idea of the total, all the neutrinos that are produced. So you can see the beryllium 7 line, which is of the order of 10% of this, but it is in the form of a line. So if you had a good enough energy resolution, you could actually measure this line, peak sticking out. We do not yet have such a detector, high resolution detector. In fact, if you had a high resolution detector, for some fraction of the time, it also decays to the first excited state in lithium 7. And so you get a second peak as well. These two are related by the branching ratio of the electron capture process. Then you have these so-called CNO neutrinos here, which are much lower than the PP neutrinos. Also, the energies don't extend that high to about less than 2 MeV. The high energy HEP neutrinos are there, which are, I showed you one of the processes where helium-3 captures the proton. They would be, I think, extremely hard to detect because they are so small in numbers. But the PEP neutrinos produce a line, and in principle, even Borexino has some sensitivity to this. But a high resolution detector would be, of course, much better in picking out this small peak intensity over the background of both radioactivity as well as the other neutrinos. Okay, so this radiochemical experiment, which is inspired by Pontecorvo's proposal, produces roughly 137 argon atom every 2 days in this 600-ton detector, and over a period of time where Davis just stuck to his task in spite of all the difficulties, he over this 25-year period showed that the neutrinos are roughly half or 1/3 of what you expect. So this is the production rate of argon per day. You can see that that's roughly half if you average out over all of this over a period of time, over a period of about 25 years. Okay, so there are also other experiments going on, Kamiokande, Super Kamiokande, then the GALEX experiments, which are basically radiochemical experiments using gallium this isotope of interest there is 71 gallium. So you produce 71 germanium, and this has the advantage over the detector of Davis, in that Davis detector had a threshold of about 800 odd keV, whereas gallium has a threshold which is of the order of about 200 keV. So it has sensitivity also to the PP neutrinos. Not all the PP neutrinos, but a good reasonable fraction of the PP neutrinos. So the fact that this could be understood in terms of the then known physics also pointed out that we are indeed finding evidence for PP neutrinos, which are the main things that are produced in the sun, which give the which are 99+% of the total reaction that take place. Okay, then Murthy has just talked about the snow experiment, which actually solved this problem of the solar neutrino problem. In that, if you looked at only the electron type of neutrinos, you saw 1/3 of them, just like Kamiokande and so on, or Davis. But if you looked at that part of the signal which came from all neutrino flavors, so-called neutral current signal, then you saw the full flux of neutrinos. So this told us that the solar model of Bacall and company was actually good. In the next slide is shown some of the why are there fewer neutrinos than expected. So that Murthy has already said. This basically depended on this was an idea proposed by Pontecorvo and Gribov, who said that neutrinos can oscillate, and then Mikhail Smirnov built on the Wolfenstein idea and showed that you can have resonant enhancement. So then this becomes really a broadband solution, because somewhere along the path of the neutrino, which can come at different energies, you can have it, resonantly change to the muon type of neutrino, which then won't be detected by a detector on Earth. So this can happen at different densities depending on the energy, as Murthy just showed. So this is a very robust idea to show that the neutrino oscillations can lead to this effect, that is the observed shortage of neutrinos that we have on the Earth. However, initially, this idea of neutrino oscillations as a possible solution of the solar neutrino deficit was not accepted by particle theorists. So there could be two reasons why you don't see so many neutrinos. One is that you have the solar model and nuclear cross sections go into it. How do you know that these nuclear cross sections are what they are really? You have measured them, but perhaps there are errors in that, and if you play with these errors, perhaps you can produce this factor of 3 difference. In fact, this was the feeling of many particle theorists. So even Pontecorvo, who actually proposed neutrino oscillations, said that unfortunately the weight of the various thermonuclear reactions in the sun and the central temperature of the sun are insufficiently known, well known, in order to allow a useful comparison of the expected and observed solar neutrino. So he was pretty skeptical of the oscillation solution to the shortage of neutrinos, the observed shortage of neutrinos. Georgi and Luke. Georgi was a theorist in Harvard, and he said that most likely the solar neutrino problem has nothing to do with particle physics. It is a great triumph that astrophysicists are able to predict this figure at all to within a factor of 2 and 3. I mean, earlier they would say that, okay, if you can get it right to factor of 10, you should be happy. Astrophysicists should be happy. Here he says, okay, even within a factor of 2 or 3, you should be happy. Yang, a very, great theoretical physicist, who actually was one of the 2 Nobel Prize winners, Yang and Lee, who won the Nobel Prize for proposing that parity is violated in weak interactions. He also did not believe in this. He said that I did not believe in neutrino oscillations even after Davis's painstaking work and Bacall's careful analysis. The oscillations were, I believed, uncalled for. And Drell says in a letter to Bacall, the success of the standard model of particle physics was just too dear to give up, because oscillations mean that neutrinos are massive. The masses might be tiny, but they are non-zero. That's the main thing. And so this is outside the purview of the standard model. You have to fix the standard model. And so they said that the success of the standard model was too great, too dear to give up. Okay, so now we come to another kind of detector, the Borexino detector, which is in fact not just found PP neutrinos, but very recently has also found evidence for the CNO neutrinos. And it turns out that the CNO neutrinos only contribute about 1% to the total neutrino flux from the sun. So, however, it's a remarkable experiment, no doubt, but it's a very difficult one where they have to deal with all low energy backgrounds. As I said, PP neutrinos only extend up to 420 keV, so the peak is somewhere around 200 keV or so. And so, what is plotted here is the events per 100 tons of the scintillator times the. So, on this is the energy plot through the electrons that you see, whereas here is the number of photoelectrons, because the scintillator is viewed by photomultiplier tubes, and you actually look at photoelectron. You can get it down to single photoelectron sensitivity, and so what is plotted here is the number of photoelectrons that you see. That's just actually proportional to the total energy that is deposited in the scintillator. This is one of the, by the way, the purest scintillators in the world, with uranium and thorium concentrations of the order of 10 to the minus 18, 10 to the minus 19 of uranium thorium per gram of scintillator. Okay, so it's extremely pure. Okay, so you see the contribution of PP neutrinos in this red line here. Can you tell me if you can see this cursor which I have? Because in this case, I think in the PDF file, sorry, I can't generate that laser cursor.
Yes, sir. We can.
You
We can see, sir.
Okay.
Yes,
Okay.
sir. We can.
Okay. So this is the contribution from the PP neutrinos, but you can see the overwhelming background of carbon-14 decays. Okay, this is the background due to carbon-14 decays, and also there is this polonium and what is that? Carbon-14 background is this green. 210 polonium is this peak here that you see. This is due to alpha decay. Bismuth 210 is this green line, this one. So there is a huge amount of background, and the signal due to PP has to be extracted from. So they have very sophisticated techniques of extracting this small signal from a huge background by saying, that this some of this background is actually near the surface. So the polonium 210 bismuth background is near the surface. Some of it is in the volume, because the carbon-14 is, of course, in the volume of the detector, and so on. So they have ways of distinguishing it, and then they ultimately fit it. And so they can extract PP flux of the order of about 6 times 10 to the 10 with a 12% error on this. Okay? So this is the majority of the flux of neutrinos. So you have roughly 60 billion neutrinos passing through the tip of your finger every second. That was what was said by Murthy and Amol, right? Sometime in the first of their lectures. Then you have the beryllium-7 neutrinos, which are about a factor of 10 lower than that, 5 times 10 to the 9. And these are measured a little more accurately, because the beryllium-7 neutrinos go up to higher energies. So this is the red line here corresponding to beryllium-7. So you have a background from other sources, but this basically dominates the spectrum in this part of the spectrum. Now, why you see a continuous spectrum is because the beryllium-7 neutrino scatters of an electron. So it's much like Compton scattering of a photon. So when a photon scatters of an electron, Compton scatters, the electron can scatter from 0 degrees to the largest angle. So the photon can scatter at 0 degrees or up to 180 degrees. And at 180 degrees, of course, it transfers the maximum amount of energy. So when the neutrino scatters at the backwardmost angle, it gives the highest energy. When it scatters at forward angle, it gives the smallest energy transfer. And so you have a continuum, you have a continuous spectrum. If you had a detector which could actually give you a line, then that would be really fantastic, because this line would just stick out from the background. And there is one such detector, but this is not the occasion to talk about it. But that has never been yet built. This was proposed by the very same gentleman who actually proposed the Borexino detector, a gentleman called Raju Raghavan of Indian origin. Okay. Then you can look at the CNO neutrinos. You see this part of the spectrum, such a tiny part. It is a factor of 10 smaller than the background. But again, by using techniques of estimating the 210 bismuth background, they have a way of quantifying that, and then relating that to the surface and so on. And they make a reasonable measurement. Of course, in the initial measurement, which was the 2014 measurement, they only put an upper bound on the CO neutrinos. Okay, but before that, maybe I should just mention that they also found the boron-8 neutrinos. Boron-8 neutrinos being the highest in energy, they have the least amount of background. And so you can see this blue dot at least the higher energies matches the experiment observation. So you have again a error bar which is even less than the PP neutrino error bar because of this background free nature in this region of the spectrum. And so this is 5.7 10 to the 6. So this is about 4 orders of magnitude lower flux than the PP neutrinos. But as you can see, it is not that much lower. It is about 3 orders of magnitude or so lower than this PP neutrinos. But that, if you integrate it, of course, over all these energies, but that is because of the E-squared dependence of the cross section. Now, the Borexino did a better job in analyzing this background of bismuth 210, and in a later paper in 2020, I think, they have, which they have published. This is a Nature paper in 2020, November 26 issue. So this is not very old, actually. This is just about a few months old, 3 months or so ago. They have estimated all these backgrounds, and they the conclusion of the paper is that the CNO neutrinos, its absence, note the careful use of words, its absence is ruled out at the phi sigma level. Phi sigma is a kind of gold standard in particle physics. So the Higgs boson, for instance, was seen at this level if you combine the two experiments. So its absence is ruled out at the phi sigma level. But of course, the presence is only at 3.5 sigma because of all these background issues. So, however, they claim a flux that has been observed at the 3.5 sigma level of about 1% of the total neutrino flux. And as I said,
you have about 5 minutes.
Okay, 5 minutes, fine. So this is roughly what I had to say. And of course, there is a bright future for solar neutrinos. There are upcoming next generation, for instance, the Juno detector, which is actually the primary goal is to study reactor antineutrinos and measure the mass ordering of neutrinos. Will also have many other goals, including measuring solar neutrinos, supernova neutrinos, proton decay, and various other things. Snow Plus is a detector also, which is a 1 kiloton liquid scintillator detector in Sudbury mines. Their main goal is to put tellurium in that and look for a neutrino-less double beta decay. But again, usually all these big detectors have also other goals and other physics that it can do, and they highlight that as well. And one of the things that it can measure is, of course, the solar neutrinos. Because just as with the 1 kiloton heavy water detector, they measured the neutral current signal. Now, instead of heavy water, you have liquid scintillator, so you have a signal which is 50 to 100 times larger, and so thresholds can go down dramatically. And so this is also one of their goals. But of course, the main goal why they're putting together this detector in the same place as they had the 1 kiloton heavy water detector is to actually measure tellurium 130 double beta decay, neutrino-less double beta decay. Okay, so I think I will not even start here, but the idea was that I will then go into now measuring cross sections of astrophysical interests. So of course you have to talk about accelerators, detectors, and methods to analyze some of these reactions at these very low energies. So I will keep that for the next lecture. So I'd be happy to answer any questions if you have them. Hello, can you hear me?
Yeah, in the chat, there are a couple of questions.
Okay. I can't see the chat, so maybe if you could
Shall I read
read them
it?
out.
Okay, what kind of nuclear reaction happens in blue stars like Regal? Is it the same as nuclear reaction in the sun?
Okay, so
Sir,
these
video,
reactions. Hello, sorry.
sir, screen share.
Okay, so
Go ahead, sir. Go ahead.
in these bigger stars and presumably which are hotter inside, reactions which take you from all the way from carbon burning to silicon burning to ultimately go to iron. These is what would happen over a period of time. So initially, the burning of carbon and oxygen proceeds fairly slowly, but as you go higher and higher, as you go to iron, for instance, then these things proceed much more rapidly. And so I think this star.
It's the supergiant.
Yeah, that goes to supergiant. That's right. But in these, I think in these blue stars, presumably you would have. I don't know what would be the what is the mass of this star. Does the person who was asking the question know? Because I'm not an astrophysicist, so I don't know offhand the star that you mentioned. What is the mass of that star? If of course it's a very light star, then it might just become a white dwarf. But if it is a very heavy star, then it could lead to further nuclear reactions and, as I said, carbon, oxygen, neon burning,
It is
silicon.
much heavier than the sun because it's expected to become a supernova.
Oh, okay. So then it would go to the stage of making iron, and then it would go to either a supernova or a black hole.
Yeah.
Yes.
It goes further beyond
So
that.
these heavier reactions would be taking place. In the sun, as I said, the CNO cycle contributes only 1%. It's a very light star. Okay? And therefore only the PP and reactions involving helium and so on occur up to roughly mass 8.
Sir, there is one more question.
Yes?
The question goes like this. In what way neutrino and antineutrino are different?
This is a very deep question actually. Uh, and to tell you the truth, we don't even know whether the neutrino or antineutrino are different particles. Okay? They could be the same particle. However, in what we can definitely say is that in beta decay, neutrinos of a certain helicity are emitted. Okay? So, for instance, if you have an electron capture or a positron emitting beta decay, okay, then the neutrino that comes out is left-handed. How do we know that? Apart from theory, there is a beautiful experiment done by Goldhaber, Sanyar, and Brodzins, which actually measured that helicity of the neutrino. So they basically transferred the measurement of a helicity of a neutrino to a measurement of the helicity of the photon that accompanies this decay process. And that way they showed that the helicity of the neutrino that is emitted in the electron capture is actually -1. So it is a left-handed particle.
You can also
Similarly,
look at the charged lepton that is produced in neutrino interaction and
that's
antineutrino.
right. You can also measure the
They have
helicity.
opposite charges.
That's right. You can measure the helicity. And that indeed was done by a gentleman, I forget the name. What is that? Not Vaidyanathan. Palathingal. Palathingal did this
Jose
in the case of
Palathengal from
Jose
California.
Palathingal. He was at that time, I think, in Michigan's university.
Yes.
And he measured the helicity of the beta particle, which told us about the helicity of the antineutrino. And that came out to be +1 within error bars.
That's right. Okay. He did the helicity measurements.
Yeah. But whether or not the neutrino and antineutrino are the same particle or not, that is a question that is a very fundamental question. And you have asked, you hit the nail on the head. And that question could perhaps be answered by experiments which are ongoing or which are planned, which look at the possible neutrino-less double beta decay. Because if the neutrino is its own antiparticle, then you can have neutrino-less double beta decay. And by measuring that, you would be able to say that neutrino is its own antiparticle. And then what you would say, of course, is that in beta minus decay, you have right-handed neutrino, Majorana neutrino coming out, and the left-handed one coming out in the beta plus or electron capture decay.
Yeah.
Does that answer your question?
Sir, there's one more question.
Yeah.
Tau neutrinos are massive than electron neutrinos. So is it more interactive?
No. It's not clear. It's not clear that tau neutrino is more massive. What happens is that the experimental bounds on the tau neutrino are very poor. And so we can only say that I don't remember how much that is, but that is of the order of tens of MeV. Okay, but that's an upper bound. It could be even 0. I mean, of course, it won't be 0 because of the way the mixing is. But experiments only give an upper bound, okay? And it's not. We really don't know the answer to this question whether the tau neutrino is heavier than the. So what happens is that when you now want to measure the mass of the neutrino, electron type of neutrino, let's say, if you had, I mean, the best detectors in the world, ideal, so to speak, detectors, then Sometimes you would measure a mass of M1. Sometimes, given by the probability amplitudes of this mixing matrix,
Yeah.
sometimes you would measure M2 and sometimes you would measure M3. Of course, how many times, what is the probability that is given? Because there are matrix elements to those, right? But if I take a single measurement, I won't be able to say whether I would get this M1 or M2 or M3. But that is what would happen. So, I mean, these masses, we don't actually know these M1, M2, M3s. So we cannot right now say whether the tau neutrino is less massive or more massive than. In any case, it is light. Okay, it is of the order of electron volts maximum. It can't be much heavier. It can't be keV or it can't be MeV. That we certainly know
Yes, sir. There
because
are
we
no
know
more.
the mass square differences. Okay, so, yeah, go ahead. Sorry.
Sir, there are no more unanswered questions, sir.
Okay.
Yes, sir. Thank you, sir, for this informative session. Dear participants, if you have any more queries, you can mail it to us. We will communicate with you. Tomorrow's lecture session link will be sent it to you to your registered email IDs. Looking forward to see you all. Thank you all once again. Thank you, sir.
Thank you very much.
Thank you.